So today's session also similar to the previous talks will have two parts. One part is the background on channel modeling. The second part is something related to research. So we talk about generally what do you mean by a channel modeling, what are the things we need to look for, and what are the basic things of properties of channel. Let's understand them from fundamentals. And the second part is I'm currently working on with my students on air-to-air channel model. So I'll tell you what I have done so far. We haven't published the work yet, but you can see the relationship between what we know, what we are learning now in the first hour will be applicable or will be relevant, and they are necessary to understand a research problem that I'm going to present in the second hour. So in fact, also wanted to mention that the talk by Sundar Vanka on Saturday is actually very timely in the sense he gave in the first slide itself, he gave a simple idea about how path loss, channel gain and shadowing, how they can be combined in a very simple formula. So now we are going to learn how do you get the channel gain. In fact, how do you model a channel impulse response? That is the key for understanding something further. And I also wanted to mention that I use the book, the content from Wireless Communications Principles and Practices by Rappaport. That's an excellent book actually. Okay, especially when you are looking for communications, I strongly recommend to use the book. There are many books, but especially for the very basic ideas about, like for example, channel propagation. This is what we are going to spend time today. And you remember the plot that Dr. Vanka showed you on Saturday is something like this. Okay, so he considered an abstract model, but I'm actually going even more fundamentals. And the reason is, I see that some of you are in undergrad school, and you might not have gone through some of these basics in a formally. The second thing is, Professor Vanka's topic is more rigorous in the sense it talks about the mathematical foundations, and that's and for that you can't go and talk about basics. So I'm going to fill that, fill the gap, and then tell you how sorry, how these ideas and how these fundamentals are helpful if you decide to work on new models. All right. So take a look at this slide for a minute, and then we'll get into the details. The purpose of the next few slides, or first this hour rather, is to understand the characteristics of radio wave propagation, and then how do we measure the quantities. Some of the quantities are metrics. So more specifically, when you look at the propagation, you will see small scale fading, large scale fading, and let's go over them slowly and then understand the ideas here. Typically, when there is a propagation from transmitter to receiver, the first thing is that we all know, we talk about the free space loss. So in addition to that, in addition to that, you will also have what we call a lot of reflections, and the signal actually will go through a transmitted signal that is sent out by any radio, will go through all these physics, reflections, diffraction, and scattering, and all these have to be accounted for. Now, how do we take into account? So first thing is, obviously you cannot go very meticulously and see how you cannot characterize each of them individually, But in general, by doing a lot of experiments, like practical demonstrations or experiments, you can capture the essence. So that is the summary here. Now we're going to look at. First is, due to multiple reflections, waves travel different paths. So in addition to typically a direct line of sight, most of the time, yeah, you can assume there is a direct line of sight, but sometimes you may not have a direct line of sight also. Okay, but ideally you can assume along with the direct line of sight, you also have several non-line of sights. So we'll go through, we'll look at them visually in a minute. To begin with, this interaction is called multipath fading, or the physics is called multipath fading. And why is that multipath fading? Because as signal travels through any distance, actually, because it's an electromagnetic wave, it travels at the speed of light, and then it will naturally have a path loss, which is proportional to d square. So that is one thing. But on top of it, you're going to see a lot of these effects, and those are reflections, diffractions, and scattering. So in general, you can categorize into two types of fading. Large scale fading, large scale propagation models predict average signal strength over long distances, and then small scale fading typically mean they are rapid fluctuations of the received signal strength over short travel distance or short time duration. So there are two major aspects. One is for long distance, for long propagation model, long scale propagation model. Second is small scale. And if you look at this picture, you will also see a basic idea of what do you mean by small scale. Okay, so first thing is large scale. Look at the blue curve. That talks about, in general, when the signal travels a long distance, primarily it captures the path loss, free space path loss. On top of it, you have all these small scale fading, and the scale actually refers to the wavelength of the transmitted signal. So here, when you say small scale, you have to keep in mind we are referring to, with reference to, we are actually using the reference of the wavelength of the signal. Okay, so that is one key idea that you have to remember. So in general, you can summarize, there are large scale aspects and small scale fading aspects. So first thing that we need to know, free space propagation. In fact, in the presentation that Dr. Ranka showed, it's very simple. In one line, or in very succinctly, you can capture this free space loss by simply saying it's a function of d power some exponent. Typically, it's d square, especially if it is free space. But if the environment is urban or more complex, then the exponent may not be 2. It's something bigger. So again, in simple terms, you can say path loss, especially free space path loss, is a function of d square. Okay. So that means you can say it's a function of d power minus 2, right? Keeping other things aside, we are only looking at the in terms of distance. What is what you call path loss exponent? You can say in free space it is 2 or minus 2. But then if the in urban environment, like there are so many buildings, or sometimes even in a rural environment, there are a lot of, for example, trees or shrubs. In such scenarios, it is also possible that the path loss the path loss exponent may be anywhere between 2 to 4, or sometimes the worst case could reach 5 also. So that means that the path loss is going to go through a lot of RF signal will go through significant losses if the environment is very complex. So remaining things are straightforward, right? But let's go through them very quickly. It depends on, of course, wavelength or frequency. Then you know the formula from lambda frequency to wavelength, which is lambda equal to C over F. Then GT and GR refer to gains of the antennas, transmitting antenna and receiver antenna. In simple terms, you can say if it is isotropic antenna, you can replace them with 1. and then PT is the transmit power, and then PR is the received power. There is also another term here, that L is the system loss. What does it mean? Something to do with hardware and other factors related to generally the antennas and RF system hardware part. But if you ignore this, and if you set GT and GR equal to 1, it's very simple that path received power depends on transmit power, the wavelength, and distance. Those are the key things. Again, I'm reviewing this for the benefit of people who haven't taken this so far. Okay? All right. And this is a little more details about gain of an antenna. That depends on the effective aperture of the antenna. And then we said L equal to 1 indicate no loss in the system hardware. So we talked about L before. So if you set L equal to 1, which means that you're ignoring any system level or hardware losses. There is also another term called EIRP. EIRP stands for effective isotropic radiated power, and that is equal to your EIRP equal to transmit power times G of T. Yeah, again, all this information you can see in the book. You are getting a quick tour of, I think, at least a couple of chapters from the book in this first hour, and these are important so that we can go to the next research topic, so that otherwise you won't be able to understand that. Stop me if you have any questions, but this should be clear actually. Okay? All right. Now this idea of path loss for free space, including antenna gain. If you include antenna gain, it is in terms of dB, path loss equal to 10 log PT by PR. Okay. And that's actually 10 log GT times GR lambda square 4 pi square D square. So this is coming from the previous slide. So if you set antenna gain equal to 1, then it's much more simplified. It is path loss in dB is 10 log lambda square by 4 pi square D square. This is very simple and straightforward. But notice, when you look into representation in dB, you're going to see a lot more than one term. We say dB, sometimes we say dBm. What's the difference between dB and dBm? M refers to in milliwatts. You're using power in milliwatts. So dBi is there. dBi used for antennas. With reference to isotropic. I stands for isotropic with reference to isotropic antenna. So same way dBm refers to with reference to milliwatt as a reference. dBi refers to antenna gain actually. So that refers to with reference to isotropic antenna, what is the channel gain. There are other things too. Okay, there are more such terms. dBi. Okay, we will see them, but those are easy to follow. All you need to do is, of course, we have. You can search on the internet, or you can search on many other sources. But keep in mind that when you're doing the computations, you have to be very clear, or what units you can add, what units you cannot. So it's important to make use of, understand the notations, understand the units very clearly. So these are straightforward. Okay. Now let's look into little more into physics. When we talk about line of sight and non-line of sight, let's review them for 5 minutes. Here, there is a vehicle. Mobile receiver is in the car, and there is also another mobile vehicle, but we are only using it for explaining or illustrating the reflection. So here is our transmitter. Here is the receiver. So now look at, there is a direct path. So that's what we call line of sight. And there are many paths. Let's look at one of them is reflection. Look at this. There is a signal here from cell tower hitting a house, and then it is reflected from the house to some other obstacle or some other building, and then it is reflected again. So that is one path. That's typically maybe one of the longer paths. And then there is another one from the building. It's reflected to the mobile vehicle, and then it is falling on like an object and getting scattered. Then one more is there is a building that is being reflected, from which the signal is being reflected, and many more. So you can see, first thing is there is a reflection, and there is a diffraction here. This is another example of diffraction is here. Then there is a scattering. So one signal is coming reflected, and then there is another reflection, and then it is going through scattering. So first thing is, you can see the complexity of it. We can draw a lot of diagrams like this. At the same time, it's difficult to capture what exactly happens to your signal. It is not possible. So the only way you can do, somehow do some experiments, do some simulations, and come up with an abstract way of capturing this physics. So no matter how you do, what you do, it's not possible to really know what exactly happens to the signal, but doesn't mean that we cannot solve problems. Okay, there are ways to do some experiments and come up with a general, capture these concepts in a generic sense. Okay. But the point of this slide is to make you understand these ideas. What is reflection, what is diffraction, what is scattering. Okay, there are some more information about these physical phenomena, and the textbook, of course, gives you a lot more details. All right. Okay. Now, there is a model called reflection, a two-ray model. This is what practically used. In fact, when I wanted to develop the air-to-air channel modeling, this is the model we are using. We start with one ray and then adding more rays later. But to begin with, the fundamental level, whenever you think about channel modeling, it doesn't matter whether it is on the ground or air to ground or air to air. These ideas, this concept is useful. So this gives you a simple means. Assume that there is a transmitter at altitude of h sub t, and there is a receiver at altitude of hr, and then you are showing only two lines, two paths. One path is line of sight, the other is non-line of, only one line of sight. What's happening is the signal is being reflected from the ground. Okay, I'll show you after 1 hour and in the next lecture how we shorted like this for a air-to-air channel model. So the nice thing is, if you understand all these ideas and spend some time, probably a couple of weeks, going through the 2 chapters in the book, you will be ready to do any new channel model on your own. Okay, so there is a tool called Insight that I'm using. It costs money. No, I think academic discount was like about $7,000 I'm paying for Insight. Maybe there are for students, or maybe there may be more discount if you reach out to the company. But in general, that tool also, it implements all this physics internally. So we don't have to worry about modeling this. But modeling on your own is also important, because understanding how channel models work and then trying to develop the mathematics behind it will help you to look at the theoretical aspects. And then if you use a simulation tool, I believe in MATLAB also it is there. If you already have a MATLAB, look for whether you can model this in MATLAB itself. Okay? So MATLAB also provides you these tools for modeling channels, and Insight is more specific for this kind of thing. INSITE. So my point is, you need to understand the concepts. You should be able to understand the theoretical modeling, how to do the theoretical modeling. At the same time, you should also use some tools. That way, you have a multi-pronged approach to develop or to do some research. But without knowing all this, you cannot do research. Okay? And the other aspect is you always have to have a theoretical component. Otherwise, anybody can do experiments. Just because you do 100 experiments doesn't mean that you are able to show something. If you want to have, if you have a hypothesis that you come up with, if you want to test, if you want to show that this hypothesis actually works, you have to have theoretical concepts and support and show how the experimental results validate or verify what you come up with, and then if there are any discrepancies, you should be able to figure out, and that is actually the research. When there is a discrepancy between theory and practice, you ask the question why there is a discrepancy and answer them. In that process, actually, you will find some interesting things. So it's not enough if you just only do the theory or if you just do the experiments. You need to do both and see the connection. Whether the ideas that you have in mind are working. If they work, then it's good. If not, then you should be able to see what is the reason, and then you refine your models. So that is the process you have to follow. So here, you're only showing two paths. And obviously, you know that the line of sight is the shortest path, and then this path is reflected. So that's why it's longer. So in simple terms, all you need to do is you need to look at for example, for example, let's say if you are computing the received power, then the received signal is coming through two lines, two paths. So you're supposed to take into account of both. So I'm not actually here is supposed to be like energy, E for energy. But for now, we will not worry about this, but focus on the general idea of how can you explain, how can you consider the reflection from the ground, or maybe from buildings, or maybe some other objects. We talked about several things, right, in the last picture. It's not just one reflection. We talked about a lot of reflections, and not only, in fact, in this case, it's not even from the ground. It is coming from different buildings and then from other vehicles. So you should be able to figure out what is the context. For example, if you are simulating an urban scenario, come up with a template. How many objects you can expect, how many buildings you can expect on the average, and then create that scenario, and we need to figure out how to model these different lines of sight, different paths. In addition to line of sight, again, line of sight is, you can typically assume, but sometimes you may not have a direct line of sight too. Okay, but if you have direct line of sight, you are sure that you get a good signal, even though it gets other signals from, or signal energy are coming from other paths will add to it, mostly destructively. You cannot assume everything is going to be constructive, but then having a line of sight is important. In fact, that is the reason why you keep cell towers at a height. Otherwise, why do you need, when you say cell tower, really speaking, the tower is just a structure. The reason you are having cell structure, a cell tower, is because you want to put the antennas on top, and that allows us to give a good line of sight. So without good line of sight, you cannot get a good signal. Typically, they are like they could be anywhere about 100 feet to 200 feet. Okay. Now you can see the very first presentation we talked about deployable communication systems during emergency times. See the value of having a aircraft airlift a base station. So more importantly, the most important result of that is, or consequence of this is, you are getting a good line of sight, especially for people on the ground. If you have a drone at a 400 feet, for example, you got a very good line of sight. Okay? And the distance, there is one more thing you have to think about. If the path takes longer time, the distance is longer, then you assume you can see that power loss is larger, right? But compared to 400 feet, thinking about speed of light, and then thinking about 400 feet or even 1 kilometer, not really a big deal. But the problem is, the path loss is proportional to d squared. So that's where you encounter loss. So how the d actually distance plays a role. Mm, The other thing is that sometimes we know that having a base station at a higher altitude gets you a better line of sight, number one. At the same time, if the distance is increasing, you encounter more loss. So probably there is an optimal height, optimal altitude, where you balance, that you don't lose so much of so much of signal loss, or don't encounter so much of path loss. At the same time, you want to have a clear line of sight. So there is an optimal altitude, and that is another reason why placement of a UAV for aerial base stations is an important research problem. Okay. But here, I'm just showing you, even though we are only looking at one path here, one line of non-line of sight, in addition to one line of sight, there may be, we need to consider practically more non-line of sight. And then we'll get into that. What do you get out of it? We will learn. In the book, actually, this problem is explained very well. The geometry is explained very well by using something called reflection. If you reflect this whole thing on the bottom, then using that geometry, you can compute all these path distances much more efficiently. So take a look at Rappaport's book, please. Yep. Hmm. Hmm. Right, exactly. In fact, really speaking, you cannot reduce anything. You can't change the physical phenomena. But first of all, you have to estimate, how long you are going to get these signals. For example, here you're getting one copy, then this is another copy, and then you get more and more copies. So there are some metrics like, we'll going to look at them. Delay spread, that's one that captures the how long you're going to get these copies. Okay, that's number one. Number two is, you cannot change the physics. You cannot eliminate them, because you cannot remove the buildings. It's not in our control. But what you need to do, you need to develop the techniques at the receiver to deal with them. Like, for example, multipath, or you can you can design a receiver to effectively collect all these signals, and then see whether you can do something constructively add them. Okay. There is, for example, there is something called rake receiver that does something like this. The second thing is multi-input, MIMO, for example. It also is a means of effectively dealing with this. Okay. So we cannot change the physics, but you need to you can come up with intelligent small techniques to build a better receiver to handle this multipath problem. But I keep telling in my class, multipath is an important problem that in communications, if you ask what is the most important problem, that this is the problem. Okay? But the more you understand, it's basically there are a lot of work done in this field. But if techniques to handle the consequences of multipath propagation is a challenge. So those techniques there are there, but there is more need. But we will talk about the thing that you mentioned. All right, here is a interesting thumb rule. It says if the environment is free space, the path loss exponent is 2. We talked about that's the minimum. Okay, free. So even in free, what's more important is in free space, that's the minimum loss you can get. But then quickly you can see the worst case is here, somewhere here, shadowed urban cellular radio. In urban setting, this exponent can go all the way to from 3 to 5. That means severe loss. 5 means severe loss. Okay, and then other things. In general, if there are shadows, means like buildings completely obstructing sometimes. And then in urban, if it is simpler, less complex urban setting, it's anywhere between 2.7 to 3.5. Within building, this is within building. So it looks like within building you are better off actually than obstructed in building, in factories. So look at these first three. The point is, anywhere it can go typical exponent anywhere between 2 to 5. So there is another way to explain path loss. Some of the books, they use a reference distance d0. For example, d0 could be like 1 meter. So you first of all compute what is the path loss at 1 meter, and then use it to estimate path loss at a distance d. So sometimes in books you can see this model as well. So now I can move a little faster so that we understood the basics. This is called log normal shadowing model. The log distance path loss model does not consider the fact that surrounding environmental clutter. So the clutter means like a lot of buildings also could be called clutter, or maybe a lot of trees, shrubs, those also called clutter. So basically he's adding a variable, let's say distribute some sort of a random variable that has a Gaussian distribution. So which means that in little more, in complex environments where there is clutter, you need to add an additional term. I hope you see the point, right? So this part is what you already know. This part is you already know. But this part is something additional variable that you are adding to accommodate for complex clutter in the environment. And there are lots of models, but we will probably look at only we don't have to review all of them, but there are a lot of common models. But typically, the model, the path loss model depends on the environment. Environment means trees, buildings, hills. So it's not the same. Some people spend a whole lifetime just working on this kind of research. And they say also 3GPP came up with standards for different environments, the parameters that are associated with it. So you don't have to do research from scratch. You can always look at standard models. So for example, if you want to know how to account for rain, how do you account for like clouds, there are standards models that are already developed. In fact, most of the time this kind of research is done by physics people. Okay? Because if we don't know how, we can't do everything. We start with like path loss models and adding some parameters to account for more complex environment. But it's a physics people who actually study what is the impact of rain. And for example, scattering could happen because of a raindrop. So people spend their lifetimes, as I said, to study this kind of thing from scratch. But fortunately, a lot of work has already been done. All right. Now I will skip some of the slides. Okay. Now I'll need to look into one more deck. So this is part 2 of the channel modeling, and then I have part 3. Part 3 is more like a research. Part 1 and 2 for the first hour. Here we are reviewing, what are the parameters, what are the some of the basics for this topic. So let's start with the concepts of fading. So term fading refers to rapid fluctuation of the amplitude in a radio signal over a short period of time. And fading is caused by interference between 2 or more versions of the transmitted signal. So we talked about multiple paths. So multiple paths will cause the interference. So they are not constructive all the time. There is possible that in some cases it is, but typically it is. You can assume that it causes actually a destructive interference. So how is that? So look at the third bullet. At the receiver, radio waves generated by the same signal may come from different directions with different propagation delays and amplitudes and phases. So this is called multipath component. So more specifically, we need to have an idea about how do you account for, or how do you model the propagation delays. And there are very specific concepts that we will be learning. Okay. So 3 types of small scale fading. One is changes over a small distance or time interval. In fact, time and distance are connected. So whether you say over a small distance or over a small time interval, both are actually referring to the same. So one is to do with the distance, and the other is about the Doppler effect. It's more to do with the frequency shift. And Doppler shift comes into picture when you are in a moving vehicle, either transmitter is moving or receiver moving, then you get into Doppler. And the third is generally, there are other things that we talked about, other physical phenomena like refractions, reflections, scattering. So those are also will cause multipath propagation. And ultimately, the most interesting thing is you can model the channel as a system, and it could be depending on how we interpret or how we design. It could be in simplest term, it could be something called a linear system or linear time invariant system, and in general actually it's a time variant. So, but if you oversimplify, it's possible that at least for some short duration, you can model the channel as a time invariant system, and then you can come up with something called a channel impulse response. So, for again, just a quick review of for those who haven't done or studied this topic from basics. So you are saying there is a transmitted signal, it's going through a channel, and you are receiving at the receiver. So one way to interpret this is you are sending a signal through a system, and you are seeing what is the output of the system given this input. So basically, you can explain the channel as a system for which you can derive input-output relationship, and that is typically done in the form of a impulse response. So basically, a channel can be modeled as a system, and its input-output relationship can be explained in the form of a impulse response function. Okay. I think that is the that is the way we can interpret. And now, what are the factors that will influence small scale fading? Small scale fading refers to small fluctuations over small intervals of time, or fluctuations over small intervals of time, or small distances. So what are the causes? What are the issues with one is multipath propagation, which we already spent a lot of time on, and then there is the vehicle of speed of a mobile. So obviously in this case we are saying we know that cell tower is not going to move because cell tower is fixed on the ground. So what is moving? The receiver. Your phone is moving because you might be in a car, for example. But when you go back to lecture 1, is the other way. If you put the base station on a cell tower, so on a drone, then the transmitter is moving, or cell tower is moving. And even more interesting is, in the case of satellite, LEO satellite, is a satellite that is moving. So far, for ground communications or terrestrial communications, we assume that cell towers are fixed. It is the phone that is moving, or the user that is moving. Okay, but some of these ideas are you can use the same concepts, with of course cognizant of the fact that the speeds are different. The speeds for when you are moving on the car is different. When you are talking about drones, the relative speeds are much higher. You talk about satellites, what speed they are going to fly? LEO satellites fly around 26,000 kilometers per hour. So when you think about Doppler shift has to be accounted for satellites. So we don't consider that much of we're not, or even the Doppler shift is encountered, which happens even when you talk about communications with drones or even with cars. But those were already you can compensate them at the receiver. 3GPP already developed the compensation techniques for those Doppler shifts that you encounter when you are traveling in a car, or to some extent for drones as well, but not for satellite speeds. For example, research showed that we also have done a lot of work that OFDM cannot handle the Doppler shifts caused by LEO satellites. Okay, even though you can try to use OFDM technique for satellite communication, it doesn't work. It's not guaranteed to work because it's the Doppler shift, that compensation techniques for addressing Doppler shift is not sufficient for satellite speeds. Okay, so which means that there is room for doing more work, both research and development. And interestingly, recently there is a new modulation technique that is OTFS, called orthogonal time frequency space modulation plus multiple access technique, and that seems to be, you can design that modulation technique in a way that is immune to Doppler shift. That's a very powerful thing. Okay? So in fact, a lot of people worked on it since at least for about 6-7 years on OTFS. It originally, the paper came out around 2018 or 2017. So a lot of work has been done, but it didn't get into the standards. The reason is even for 6G, potentially maybe it may come in 6G, and the reason why this OTFS didn't get into 3GPP so far is because the industry says that they already spent a lot of money and efforts, and then in 5G, and then they still want to make sure that their investments are protected. So it will take a while for new techniques to get into standards. The other important thing is to learn here is, you may come up with a great idea, but it may not see the light unless it gets into standards, and that depends on other factors, not just about technical talent, technical superiority, but sometimes it has to meet the requirements of the industry. Okay, let's look into quickly the other things. So here are the factors that we need to consider. One of them is speed of the vehicles, other is of course bandwidth, and other is not only the speed of the mobile receiver but also the surrounding objects. Yeah, but in general, no, not that. Actually, no, we can typically, let's assume that they are like, we only consider the relative speed. So we are okay if both are moving also. But the thing is, different, yeah. Will be higher, or yeah. But the way they do something called pre-coding technique. Yeah, basically you are giving some sort of a gap. Yeah, right. Yeah. And the pre-coding technique, it depends on how much Doppler shift you are expecting, but the kind of pre-coding that we have, the length of the pre-coding is not enough, not sufficient to handle larger thing. Yeah, larger Doppler shift. Will become smaller, and then at least at this point, the standard is did not. There is a limit on the pre-coding length. And if you arbitrarily include, there are other issues that we encounter. Yeah. Say again? Yeah, cyclic preface will work for certain length, so smaller Doppler shift. But I believe the Doppler shift that we encounter for satellite speeds is almost like 200 up to 200 kilohertz. So for that, I don't think OFDM. Yeah. But there's a good solution, but it's not yet gotten into the standards. So OTFS, if you design those resource blocks, like the resolution of time frequency blocks, if you design them appropriately, then the impact of Doppler shift is not there, won't be there. Yeah, it's the same. Yeah, it's right. That's true. It is the same, but but you need to design those resolution levels, expecting what kind of Doppler shift you can handle. In fact, probably we'll talk about that in the last class on the last day. So this gives an idea about the idea of Doppler shift in little more specific details. So what it refers to is, because of Doppler shift, your received signal frequency, especially when you are in vehicles, because of motion, due to motion, is going to be different. Your transmitting frequency is different, received frequency is different. That means, your receiver won't work. Receiver reception techniques or demodulation or decoding techniques won't work because you're getting a different frequency. And not only that, it will also cause intercarrier interference. This causes interference in terms of frequency terms. And okay, so the shift means frequency shift. It's proportional to the speed and direction of motion of the mobile. And in simple terms, this diagram explains very, very well. So when you are the original path, when you are here, when the vehicle is here, this is the path. Think about this is the source or transmitter. You can think of a 2D. Even though you are seeing this picture like this, think about like a 2D. So there is a source, and this is the receiver, and this is one path. And then when your vehicle is moving to Y, it has a different path. So in this case, you have different longer length, and now it is shorter length. Or if you go the other way, if the vehicle is going the other way, you will see again the path is going to be increasing. Here, if you from X to Y, the path length becomes shorter, but if you go the other way, it increases. So based on that, if you can compute the delta L is a difference between the two paths, X and Y. And if you put that, then delta phi, which is a phase change, you can compute phase change equal to 2 pi delta L by lambda, and that explains the connection between or the relation between the phase change because of the change in location. And it of course it depends on the speed of the vehicle and how much distance you travel. But again, this is a fundamental problem, and it is in many books you can see this. And okay, now here is what really we want to do, what we are interested in. So with all this, what we really want to do, we want to develop a channel model. So what do you mean by channel model? You want to bring the input-output relationship between the transmitted signal and the receiver signal. So that is the essence of all we talked about. Okay, and how do you do that? What really we want to do is express that relationship in the form of a channel impulse response. So what do you mean by channel impulse response? If you have a system, and if you give input as an impulse, if impulse is your input, what would be the response? It's very simple. Yeah. But then you need to make a connection to what we learned so far, and understand how do we build such a impulse response. And there are a lot of papers on it, so it's not a difficult thing. A lot of work has been done, but our goal is to actually get an idea about how do you build a channel model. Okay. So channel model is ultimately we want to come up with an impulse response of the channel that explains the relationship between input and output. X is the transmitted signal, Y is the received signal. Okay, so whether it is air to air channel or air to ground, all we want to do is express that or model that relationship in the form of a system. And when you do that, what happens? What is the result? You can say if you say H is our channel response, impulse response, is a function of distance and time. And they say later, some of the detailed examples. Obviously, distance and time are related, especially if the vehicle is or the movement is constant. Suppose the car is moving at the same speed, constant speed, then it gets simplified. But in general, it's a function of distance and time. So look at this. This is the key. If x and y could be expressed as in the form of impulse response, then y could be written in terms of x convolved with the impulse response. That is the essence of this, whatever we learned so far. So our goal is to whatever channel model we are building, are interested in, can we express that as an impulse response? Can you describe the channel as an impulse response, which is true? And then the other thing is it time variant or time invariant? Because if you simplify the model with lots of assumptions, you can say you can express that as a time invariant system, but in most scenarios it is time variant. And can you see, if you understand what is a causal system, then you can see how this simplifies. The upper bound becomes t instead of infinity. If you know the definition of causal system, think about it. Probably will give you that as a question mark in the homework. Yeah, I won't get, it's just some small thing, but if you are able to understand that, that's good. Yeah. Then in order to build such a response, such an impulse response, what kind of things we do? For example, as of now, my students and I are working on developing a model for air-to-air channel, air-to-air communication. That means drone-to-drone communication. So to do that, one option is start with simulations. So as I said, we use a tool called Insight. So what do you get from the experiments? So one of the metrics that we need to measure through simulations is called power delay profile. And by the way, I'm not an expert in channel modeling. So what I do is I found a professor who has spent his whole lifetime on channel modeling. So he is helping me. I'll bring his name. I'll discuss that when I show you in the second half of the lecture after the break. So if you don't know something, what you need to do, if you're not, because we can't be experts in all fields, so what we do is you need to collaborate with somebody else who is very specialized, who has expertise in that field. So for example, in many situations, sometimes we get into some mathematical scenarios, and for which we need some help. So we go to mathematics professors. It happened to me many times. In fact, like graph theory is one example. The other example was I was doing some detection and estimation problem, and such problem has not been solved before. So we reached out to I'll give a little bit of context to that. We were working on ranking a sensor observations, right? Because some of you are working in sensors, I can tell you. We are working on something called ranking the sensor observation, because suppose you have thousands of sensors, and you're supposed to communicate with the faraway sensor fusion center, then it's difficult to collect all this number of sensors and transmit all of them all the time. So one idea is that we came across is, how about you pick top 10 observations that are important, significant for the whatever phenomena whatever research you're doing, whatever phenomena you're trying to observe. So that question that we have is, what is the PDF or probability distribution function associated with the first rank? So look at this. Even you assume that the sensor observations are following some Gaussian distribution or something, but what we are interested in is, what is the nature of the first rank? So we're only looking at the rank 1 of observations or highest ranked observation, and we want to study what is the PDF corresponding to that. And I didn't know how to work on this, so we reached out to mathematics faculty. All right. So one of the metrics that we need to work on is something called power delay profile. What do you mean by power delay profile? It addresses the small scale fading, and of course also the distance too, but more primarily it addresses the small scale fading. So PDP of a channel or power delay profile of a channel is found by using the spatial average of these what is HP? HP is the channel gain. H refers to generally H of t, tau refers to channel gain. Or in other words, we are looking at HP stands for the, I think it's sufficient, it suffices to say we are referring to channel gain. So if PT is the, and it has two parameters, t comma tau. So tau refers to the delay. T is the transmitting time and tau is the delay. So what we expect is when you transmit a signal, you are going to get multiple copies over certain duration, and that is your x-axis. In y-axis, you are saying what is the received signal strength or received signal power for each of these delayed versions. So in general, this is the meaning of this. If PT is the, PT has a, transmitted signal with a power P has a time duration much smaller than the impulse response. Actually, think of PT like a pulse. So if you have a small pulse, and that's how you transmit anyway. Remember, when you're transmitting, you're not just sending, you're holding the signal for a while. So here PT actually refers to the pulse. And if the duration is smaller than the impulse response of a multipath channel, when you say what do you mean by the smaller than the impulse response of a channel, you're talking about how long you are getting the delayed versions of the signal. So when you send one signal at the transmitter like a pulse, you're going to get multiple copies. But how long? That is the y-axis. That's the x-axis. So they say the received power at various delays can be estimated or measured by technique called channel sounding, and through simulation you can actually plot. So for example, in our case, we haven't modeled anything. With simulation you don't have to model anything. Well, let me step back. You design the terrain. Like for example, we create buildings. You define how many buildings are there at what heights. Those we do, but we are not writing any equations. Okay, we're not. That's what I meant by not building anything. So you create the environment and then decide the distance between a transmitter and receiver. Then all these reflections will happen. This tool will take care of it. So it will give you this data, this power delay profile. So all you need to do is how to measure the power delay profile and plot the graph corresponding to the power delay profile, and that's what we can do through simulation. This is one of them. This is one major parameter that we need to do. So initially we are doing through simulation, and later we can come up with a theoretical model because we know what is power delay profile, power delay. In fact, in simple terms, you're measuring for all these non-line of sight components. For each of the non-line of sight components, which will reach the receiver at different times. For each of those non-line of sight paths, you are computing, you are measuring what is the power. Yeah. You get yeah, right. You get a multiple copies of that. Right, exactly.
And now we want that to tie up path.
Yeah. So yeah, that's true. That's actually true. In fact, when we one way to interpret that is the point that you mentioned is to begin with, you get the line of sight, you get a best signal, and then it tapers, right? So the question is, when do you stop? one way to do that is, in fact, again, my professor, my collaborator told me that when we actually doing the simulations, we got about 25 paths, and then see that, think about it, 25 paths for a typical scenario. I'll show you what scenario I did, and out of that, one thing you can do is, if the received power is, let's say, below certain threshold, you can ignore. So in our case, maybe about 15 things you could ignore. Even you don't ignore, the signal will be so small at the end. So basically it tapers drastically. That's right. Yeah, that's true. Now, the idea is, if it is too small, like below -100 or -110, even it is there, it doesn't really impact much. But you're right, in general, it can go for a longer distance. So as I said, 25 paths, 25 non-line of sights we were able to see, we saw. But generally the idea is to understand how to measure this, and more importantly, how to use this to develop a channel model. In fact, we are not even there yet. I'm just showing you. I will show you in the next hour what all we did, but we are still in the process of developing the channel model. So we'll do very quickly, and then and how do you measure this? These are called channel sounding techniques. In simple sense, we won't need to go through in detail, but in simple sense, you're trying to send like a pulse or an impulse, and then trying to measure in different regions, different locations rather, to account to you are measuring the received power at different distances. So that's the basic idea of channel sounding technique, but these are the little more detailed techniques. Now, for example, here is one. One technique is called direct RF pulse system. So you are transmitting a pulse like this to the receiver, and then at the receiver, the signal is amplified and detected using envelope detector. If you remember any demodulation technique, you will amplitude demodulation technique, you know what is envelope detection. And then it is detected and stored in the receiver, and then you can average the received power at over the time. That means over different quantized delay values, you are measuring the received power. So I think that's enough for us to understand the concept of power delay profile. Okay, you are basically capturing the received power at different delays, and the delays are coming because you have multiple non-line of sight, and the longer the non-line of sight, the longer delay it will encounter. And there are also a few more terms, so I'll skip this, and then this is more important. What kind of parameters we are interested in? We talked about what you call power delay profile. There are a few others. Yeah, we can. What's the time? Okay, 11:30. Yeah, let's take a break. So I'll wrap up this in the second half, and then go into peer-to-peer channel model. Yeah. model. No. So in general, these are the time dispersion parameters, which include mean delay. Basically, they're all about delay. Truly speaking, you can understand the delay in terms of simply by looking at what is the time at which the main signal or the line of sight signal arrived, and then what is the last non-line of sight arrived. So that is what is called the maximum delay. To express that in a more quantitatively using some metrics, you need to think about what is the mean access delay, RMS delay spread, and access delay spread. So spread is basically the maximum delay between the first line of sight, first signal, which is line of sight, and the last signal. Okay. And as we know, as Dr. Prakash also mentioning, there may be many paths, but not all of them are significant. Only certain paths are significant because they have higher received power. For example, if the received power is too small, like below the threshold or sensitivity of the receiver, then they don't mean much. So I hope you got the main idea. So let's look at these terms a little more clearly. And the other things are frequency related. Okay, and there is a beautiful connection or some sort of relationship between time and frequency things. You're going to see them in some of them in this presentation. So these are the parameters that we need to know, and then see whether we can use them in modeling the channel. Okay, that's not, in fact, that's a challenging point. So these things can be measured through some experiments or simulations. For example, delay spread. How do you measure? You can conduct an experiment, things like that we talked about before, like this. These are the three things that we can do to kind of come up with to measure this, to measure the delay spread, for example. Okay, the techniques are called like sounding techniques. The other option is, so by the way, these are real experiments. Another option is use a tool like the tool that I mentioned, Insight, to model some sort of a terrain, meaning that you're putting certain number of buildings or certain vehicles on the ground, creating here is the cell tower and here is the vehicle. So you are modeling the terrain, but your model is as good as your design, meaning that it will not reflect the reality. It's difficult to reflect the reality, and you don't know when you go to, like, for example, the center of the Warangal city or Hyderabad city. You cannot accurately depict them in your simulation, but you do your best. And I'll tell you how I did in the right after wrapping up this. The other option is those are some of them are experimental, some of them are simulation, and then ultimately we need to end up with a theoretical model. Otherwise, it's not complete. So how do you translate? The key thing that we are working on right now is, okay, these are the parameters of interest. Then how do you use these parameters to put in the channel model? That is the crux. Okay? And I've been working on it for 2 years, meaning that we are doing bunch of experiments or a bunch of simulations. And as I told you, I'm talking to a professor. His name is David Metallock. He's in University of South Carolina University. He's an expert in this channel modeling field. So I'm getting his help, and together we are working on this. Okay, and because A2R channel models are oversimplified. For example, people use just a line of sight, free space. You don't need to do anything else. But that's what we are objecting. Our goal is to say, for example, at what height you can assume you have a free space. Let me explain that for a second. See, let's say this is about let's say 10 kilometers. Okay, I'm scaling this. The distance between the ground to the ceiling is about 10 kilometers. And then small drones, we know as of today, they will fly about 100 meters at a height of 100 meters. At 100 meters, we think about some distance like this table or this podium. So at 100 feet, there will be buildings which may be 50 feet or 60 feet, or even it's possible, 50 feet building is possible, even 60 feet is also possible. So you will get a lot of reflections. So when the drone is flying at 100 feet, you expect a lot of reflections. So obviously you cannot ignore multipath. Okay, and as of today, such models are being developed. There is no standard model for even for 100 feet. But when you go to the altitudes of air taxis, we're talking about 1 kilometer and more. And there was no need to model channels for drone to drone at that heights until now. There was no need. There was we didn't find use cases. But now that there are use cases, one idea is, oh, let's assume free space loss. That means you're ignoring all these multipath things and all that. Can we do that? Can we afford to do that? Especially, you know that vehicle-to-vehicle communication is such an important aspect. Then you cannot ignore the multipath propagation. Okay, and not only that. Before coming to the last point, what about then commercial flights? Commercial flights, we never had to worry about channel models, because what height they are doing, flying about 30,000 feet or 40,000 feet. So divide by 3, you convert into meters roughly. The rough estimate is 30,000 meters, like 3,000 kilometers. Okay, right? 30,000 feet divided by 3 is about 10 kilometers. So at that height, free space is okay. In fact, there are other problems. Dr. Prakash and myself were talking just now. Other issues are, if you want to come up with a channel model, first of all, it's not necessary, because I don't think today a pilot is talking to another pilot over the phone or even data. We don't create a network of all the commercial flying. There is no need. We talk to satellite, and through satellite you're talking to the ground control station. If you want to talk to another pilot, we talk to through the ground control station, not directly. Number one. Number two is, the issue is, you can assume free line of sight or free space. That's not a problem, but more importantly, you need to look at absorption of signal through cloud and rain. Those are more important. Unfortunately, that such models are already developed. For example, what is the loss associated with rain or cloud or fog? Those were already available in ITU standards. So once again, we don't do that. It's typically atmospheric scientists, those guys do that. So my point is, it's a new area. Air-to-air channel model, new area. You cannot just blanketly say, oh, let's use free space loss. That's exactly what we are objecting, okay, in my group. And it's a evolving thing. So what we want to do is, starting from, let's say 200 feet, 400 feet, 600, 800, at different heights, at different altitudes, what will be the channel from air to air? We're talking about when multiple drones are flying, what will be the channel model between two drones? Let's say one drone is here, another drone here. So we will look at the distance and then try to vary the distance between the transmitter and receiver. Okay, and then the altitude, change the altitudes, and even you assume, you oversimplify and say, oh, they are flying at let's say 1 kilometer, and then they are the same height, and then the distance between transmitter and receiver is also you can vary. Even you do oversimplification, still it's not a done deal. It's still a lot of work has to be done. So the way we are approaching is, since we know these are the parameters that are of interest. Yeah, air turbulence, that also we're not done. In fact, we didn't even consider. We can account for losses based, because we have some thumb rules or empirical results or empirical models. But key thing is, using this knowledge from Rappaport's book, we want to see, can we develop a two-air channel model? Okay, that is the new research that we. All right. So look at, even for me, I never had to deal with this. I read this from papers, but I never had to work in meticulously. So the first thing is mean excess delay. It's like a mean. Basically, you think like it's a spread. How I talked about what are we interested in? What is the spread from the time you receive the first signal to the last signal? What is the delay? So for that delay, see, look at this, there is a known metric, mean delay or mean access delay is something called first moment of the power delay profile, and that is it includes not only the, think about tau k is the delay, you're dividing total delay into segments, tau 1, 2, 3 and until the whatever until the end of the delay maximum delay. So starting from 0 to maximum delay, you're giving into segments, and each segment you're saying you're giving a name, tau 1, tau 2, tau 3, tau 4. Basically you're discretizing, it's a continuous thing, but you're discretizing. And then notice you are multiplying with the power. So what is the power you're talking about? What is power p of tau k? What is the power that the signal is received? For example, let's say you have let's say total number of values for k equal to 5. So you're saying starting from the line of sight, what is the next null line of sight you are receiving at what time? That is tau 1. Okay. Next line of sight is at tau 2, is coming after tau 2. And what is the power associated with the second null line of sight? Okay, I hope you gathered this. So yeah, it's like harmonics, but since this is all time domain, we are only looking at time domain. So it's exactly like that. Yeah, but you're discretizing, like, just like the way you discretize continuous frequency into discrete components, you're doing the same. But this is one term. The second is second moment. I think you can call that as RMS or standard deviation kind of thing. So this is like a first moment, this is a second moment. And maximum is, yeah, what's the maximum delay? So this is these are the things that you are extracting from the power delay profile. Okay, until now it is fine. The next question is, okay, how do I use this to model the channel? It is done for ground communications, but we're still working on it. Okay, so this is actually research in progress. We haven't published anything because we want to make sure that all the results are validated. It's not, they have to be meaningful, they have to be useful, and they have to be verified before we publish anything. Okay. Then the beautiful concepts I would like, if you spend some time, you will really benefit in the context of channel. One is something called coherence bandwidth. Follow this. You talked about delay. I think we spent a lot of time, right? We understood what is the delay spread. It's purely in time domain. We also learned about power delay profile. But let's look at the second thing. We say is the frequency range over which channel effects or channel parameters going to be the same. So what we are saying is, what is the frequency range of frequencies over which the channel behaves exactly the same way? Basically, you're looking for in terms of frequency in frequency axis or in terms of bandwidth, how are these channel characteristics are going to vary. So, and then you're saying, can we come up with a way of for identifying the bandwidth over which the channel is going to behave exactly the same? Because otherwise, yeah, let's go further before we delve into this. So here, let's say, in other words, where the channel is considered flat over this bandwidth. So normally, channel is not going to be flat. Channel is going to vary over the frequency. Just like the way we call channel is going to vary over time. It's time variant. The same way over frequency also, it behaves different for different frequencies. So we are now asking, what is the bandwidth over which the channel behavior is going to be constant, and that is what we call flat. I hope you see the point. Okay, you need to understand the channel from both time and frequency, both sides. So for example, and this is this connection. We learned about delay spread just now, right? Now you don't have to do anything more. You can say with some assumptions. So for example, it says if BC or coherence bandwidth is defined sorry, there's a small typo here, defined as, ignore this if BC is defined as the range of frequency over which the frequency correlation is above 0.9, that means you're giving a threshold. You should you know, instead of asking a perfect matching, you're saying the channel is with plus or minus some delta, it behaves flat. Then the coherence bandwidth, so this coherence bandwidth is also by thumb rule. I didn't derive anything, okay, this is from the book, so it's not derived, it's like a general thumb rule, is that if sigma tau is the RMS delay, then the coherence bandwidth is 1 over sigma t, sigma tau with some constant. This 50, no, I'm not deriving how this 50 came, this is more like a thumb rule, but in general you can say the coherence bandwidth is inversely proportional to delay spread. That's the key thing that you need to know. Coherence bandwidth is inversely proportional. That is the key idea that you have to learn in both cases. You know? So it depends on what is your threshold. So if the delay spread is longer, then this becomes small and vice versa. And please read these terms, try to understand more about, you know, pick your Google or whatever and try to make sense of these terms. Not just as a definition. I tell my students, you can read them, and but also you can try to understand the definition, but that's not enough. The more you try to understand the meaning of it, not the syntax, the semantics of it, then you will appreciate. For example, you can ask the question, why is this relationship? Why is this inverse relationship? Okay, then yeah, the other thing is, yeah, so earlier we were talking about bandwidth coherence, right? In somehow you know that it's clearly related to frequency. Now the other term is coherence time. Doppler spread and coherence time are parameters that describe the time varying nature of the channel. So once again, this is another Doppler spread is, if you define FM as a Doppler shift. We talked about Doppler shift before, but here maximum Doppler shift is FM. Just like the way we analyze the signal in time domain, because of multipath, your signal is coming, even though you're sending one signal or one impulse, you're getting multiple copies of that. Same way, because of vehicle in motion, you're seeing Doppler shift. But Doppler shift also is variable, it's not a fixed thing. Because if you look at the one of the previous diagrams, you will see that the distance is not going to be the constant, you know, here. As you move, you are getting the path length is going to change. So when path length is changing, you get different Doppler shift. So the Doppler shift is not constant, it's varying as you're moving the vehicle. Even though velocity is constant, your path length is changing, and that path length, because of the path length, all this is going to change. In case of satellites also, actually, even though satellites are moving at a constant speed, probably that also is not correct, but let's assume satellites are moving with satellites. But then your relative distance, relative position, it has the line that you are connecting from the vehicle to the satellite will have a different slant. So which means that theta is going to change, the direction of what you call from the plane, from the horizon, from the ground, the angle is going to change. Because the angle is going to change, you're going to see a different distance, just like this way. So which means that your Doppler shift also is not constant. So that's the reason we are looking at what is the maximum Doppler shift. Yeah. So here I wrote just say coherence time. What is the meaning of coherence time? Time duration over which the channel impulse response is invariant, is fixed or flat. Basically, I think right term is, what is the duration over which you can expect the channel response to be time invariant. Actually, in general, it's a time variant channel, but you're looking for what is the duration over which the response can be considered, assumed to be invariant. So all these are factors that we need to consider when you are developing a channel model. Okay, and that depends on the Doppler shift. You are saying delay spread, Doppler shift, coherence time, coherence bandwidth. So you saw the 4 parameters, and they have a connection relationship among them. Okay, we'll quickly wrap this up and then go into my research that I'm going to present. So everything is about small scale fading in this section, in this second half of the first lecture, and then here are the different types. Flat fading is when bandwidth of the signal is smaller compared to bandwidth of the channel, and delay spread is less than symbol period. See, this is the point. Delay spread, if the delay spread is smaller than the symbol period, what do you mean by symbol period? The time it takes for you to transmit a symbol, one symbol. So it is called flat fading if the delay spread, you understood, you know what is the delay spread, right? If the delay spread is smaller compared to symbol period, it's called flat fading. Otherwise, it's called frequency selective fading. In the same way, if we talked about coherence time, and coherence time is less than symbol period, we call fast fading. Otherwise, it's slow fading. So it's not, I explained only the terms so far, okay? You still need to review this, understand the terms very clearly to understand, to learn the behavior or characteristics of the channel. For example, what do you mean by flat fading? What do you mean by time varying channel? These take some time. It's not just one lecture is not enough. If you have already, for example, typically if we give a lecture to students who are already thoroughly familiar with all these techniques, all these terms, then it's different. But I'm actually making sure that you are learning something from this class. So intentionally, we are reviewing the basics. Okay. Now, having done all this, so now I'm going to basically skip. I just wanted to make sure you understood these terms, and let's get into the research that I'm currently working on. These slides are from the textbook, and I can also give it to you. Dr. Professor Sai Prakash is going to share with you. Yeah, these are partial results. In fact, we haven't finished, and we have been working on this for nearly at least 18 months to 2 years. And the professor I was referring to is Professor David Metalak, who is from University of South Carolina, an expert in channel modeling. And in fact, my understanding is that his paper on air to ground channel model received so many citations, and I think that brought him, made him that was the reason, that was the I think it is the reason why what he got his fellowship. He became an IEEE fellow, and people who are recognized as IEEE fellows, they have done something fundamental, and they received it. There are a lot of citations, and the work has become so valuable. Okay, so keep that in down the lane. If you do some work and a lot of people use it, then it will make your work very valuable. And this is my master's student who graduated recently. Yeah. So the reason we are studying air-to-air channel model is because we are expecting advanced air mobility services like air taxis and air ambulances in future, and we should have a clarity, we should have a clear picture of are we going to see clear line of sight, or at what height? And then if you need to consider multipath propagation or multipath aspects, then how do you take them into account? And once you have a reasonable channel model, that will give us some ideas about what kind of path loss and what kind of how much communication range we can expect, and then also if there is multipath effect, then how do we address that? How do we deal with that using the known techniques? Like for example, multiple input, multi output, and maybe different new modulation techniques or new decoding techniques, new receiver design and all those. But in general, I think we just want to come up with a good, reasonable estimated channel model. So this is the outline. In fact, this is from her thesis. She presented her thesis, and I took it to come up with this. These are all the applications. In fact, we don't have to get into in detail. There are many applications like this, and we kind of discussed this a few times in the class, in the previous classes. And these are the issues. And here we already talked about in the previous half, but it's a quick summary. Fading means what? Fading is required because you want to have an estimate of channel gain, and more importantly, we want to see an impulse response representation of the channel. And so we need to take into account small scale fading and large scale fading. Large scale fading path loss that we already know, that is part of this. And shadowing refers to like big obstacles causing the signal not to pass through or obstructing the line of sight. So these are the large scale effects. Small scale effects we talked about. Time and in the time perspective, it's about delay spread. From a frequency point of view, it's Doppler spread. Both are necessary. And these are, when we talk about aeronautical communications or airborne networks, there are channels. These channels are important. Ground to air, air to ground. Maybe we can assume pretty much same. And then air to air is a new topic. Air to air is not addressed so much. And these are the things we need to consider. Antenna characteristics, propagation effects, multipath, environmental factors. The environment means, how do you take into account like rain and cloud, dust in the air? In fact, we don't, as I said, we don't need to go to that basics, or we can always take existing models for understanding the impact of environment. And then more importantly, this is also critical. How do you validate? How do you start? How do you come up with this design? How do you model them? And where do you begin actually? Do you start with simulations or experiments? There are many ways to do that. You see, the reason I covered all those things are so that you are ready for this talk. Okay? Now, so what is the importance? Suppose you come up with channel model, so what? This is the same question you have to ask anytime you're doing research. The first question is, why are you doing? In fact, that's what happened when I published my first paper. Conference paper is slightly easier. They accepted my first paper in 6 months. Started PhD. I published. I presented a conference paper, and it turned into a journal paper. The question was, who cares for this? So you have to explain why your problem is important, why someone cares. What do you expect? Where do you want to see the use? So here are the reasons. With a channel model, it doesn't have to be perfect, but at least a reasonable channel model will allow us to figure out to predict the performance. What do you mean by performance? I think when I was talking to some student, I specifically asking, what do you mean by performance? Okay, like I think a good example is people tell, oh, he's a great guy. So what do you mean by great? In what sense? Is a very tall guy, or is a tall person, or it communicates well? He or she communicates well. You need to go into basics and tell. So here, when you say, I want to improve the performance, you need to answer this question. In what context? What is the metric? Is a BER. So for everything you want to measure, you have to have a metric. Then other things are, this is a link performance. So link performance typically BER. BER is a good thing. Anytime you want to say what's the performance of a communication, this is one of the things that you do. Then throughput and latency. Throughput is data rate, and latency is the delay, round trip delay, for example. So for a good example is, if you are working with the geo satellites, your round trip time is large, and suppose say you are sending a message to Mars. Now what's the round trip time? Like 10 minutes, I think. Yes. Say again. 28, maybe round trip time, right? Yeah. So very good. You looks like you're tracking that. So I remember it's about roughly about 10 minutes for each way. Okay. So the reason I was told you, right, I was working on a small project, and then say, if you want to send a message and on the rover to the rover, and then there is a ditch in front of it, you have to give enough notice for it so that it doesn't fall, at least 10 minutes or 14 minutes. So latency is important, but for LEO satellites, we are good. This round trip time is not bad at all. You can have a LEO satellite based voice communication, and latency is reasonable. The third is, the other is a model, a theoretical model or even empirical model will help us to reduce the actual measurements, but ultimately at some point measurements are also important. You cannot come up with only theory. To validate it, you need to do some real experiments. But how many experiments you do? Like for example, in the simulations, you can say, oh, I want to keep the transmitter and receiver at let's say 1 kilometer, and then change the distance from 100 meters, 200 meters up to 2 kilometers. But how many experiments you can do? It's costly, but we need to do at some point. And then maybe one idea is what we do is, whenever we do the experiments, we post all the data and make it available to public. There are such platforms. IEEE data port is one thing, and there even NIST. If you suppose want some data, then you can connect with some standard bodies, and they will provide the data for you. I will go a little quickly. So these are the three models, and ray tracing is the one we are using because we have a tool called Insight, and there are other things. You can conduct experiments. You can use ask machine learning to generate the data for you, right? And then ray tracing is something that we are using. And what kind of things you have to set up? You resolve simulation, right? So look at this. Now you will be able to appreciate all these things. Where do you place the transmitter and receiver? I was showing you here a transmitter and receiver here, but that's exactly what. Distance, altitudes, and what kind of paths? Line of sight and non-line of sight. But how do you know line of sight? It depends on where do you place the buildings, okay? And the altitude of the buildings. More importantly, when we were doing all this, and then I was talking to Professor Metalak, and then he asked me, what about material? Your permittivity or when you reflect the signal, you have to consider the permittivity of the material. See how meticulous you have to manipulate. You have to plan. But this is how to develop a channel model. All these things have to be done. As I said, we already spent a year or more than a year, and here is now comes the crux. Here is the transmitter, the geometry of line of sight. And where is this coming from? From textbook. We didn't invent anything. Okay, you put a building and say, let's start with one. Then you put one more, and then see one more. And change the material of the building, concrete or something else, right? And then my student, without even by herself, she put a bird here. She said, why not an obstacle in the airspace? So initially we didn't. I didn't think about, but she herself, my student, her name is Sudeshna, she put this and said she also considered the physics of reflections and refractions. It could be another vehicle. So what exactly happened was, when we were sending this data for the professor for validation, or just asking for input, he was telling at after 800 meters or so, you shouldn't be seeing any reflections. But then we told him, I was looking at the data and see where are these reflections coming from. You're not supposed to reflections at a very high altitude. Those reflections are coming from some other obstacle that she put in the simulation. Okay, so all these are clear, right? There's nothing. But look at the parameters. So you need to, if you see, you have to be very precise. When you, especially those students who are new to research, you're just starting your research career. You need to be, look at the textbook. For example, if you look at the Rappaport book, you will see all these parameters in some sense or other. Or look at some other paper. See what parameters they are configuring. Scenario, urban, simulation frequency. Obviously, you need to know bandwidth. And what earlier we were talking about, it could be a pulse or impulse, or it could be a sine signal. And in the tool actually you can configure all this simulation area, and all this have to be carefully done. Height, total height is 3 kilometers, transmit power is 30 dBm. You can calculate in terms of watt. And receiver threshold is -109. What does it mean? Notice the units. Okay, what do you mean by receiver threshold? Receiver threshold is if it is below this, then you can ignore the line, especially for the null line of sights. And antenna type, you could give omnidirectional, that means gain is 1. And then polarization is, this is also an important thing. In fact, vertical and horizontal. Vertical means your signal is traveling, wave propagation or wave front is going in one direction, or if it is horizontal, there are two polarizations anyway. It could be angular also, but you need to define this. And these are, look at the, if you want to look at the textbook or Google, and you will see that when you see a beam like a radiation pattern, and you're looking for half power beam is beam width in terms of angle. Okay, in terms of angle, what you're configuring this. So what does it mean? After 90 degrees, your maximum power is going to be reduced to it becomes half. That's the half power. Beam is the angular angle at which, after 90 degrees, if you assume at 0 it is maximum, at 90 degrees is going to be half power. Same thing with there also called null beam width. Gain, this is I think this is the antenna gain, dBi is. So look at each of those parameters and learn about all this, the meanings of all this. And you're supposed to configure, especially you buy a tool, if you have a tool, you're supposed to configure. And then look at, this is what the student actually designed. She kept a bunch of buildings, and X is the transmitter, Y is the receiver, and then she put some obstacles, something like this. These are all it's actually 3-dimensional, okay? So let me show you, here is the little more clarity. These are at different heights. So look at them, what's the maximum height? 800 meters. So she is considering buildings of height 800 meters. Well, it's actually, the building heights are only 300 meters, but the obstacle heights are 800 meters. That means obstacle means they are flying objects. They can be anywhere, like birds and other aircraft. But the highest building is 300 meters. So this is the kind of shape that she has given. There is two obstacles, right? One is at 800, another is at 730. X is the transmitter and Y is the receiver. So this is a terrain model. It is easy to do. Once you know how to use the tool, this can be done in the simulation. But key thing is, set up the configuration and then start doing the experiments. You can measure, you can get line of sight, non-line of sight, how many non-line of sights are there. All this is done by the tool. So it uses this to figure out how many, depending on where you kept the transmitter and receiver, it gives you all the reflected components or non-line of sight paths. And then it gives you all those power delay profile, delay spread, RMS delay, all those things. I think, let's see. So one more thing is, you can make, to make it more interesting, how do you define, how do you figure out where to put the buildings, or what should be the heights of the building? And she actually considered a PDF of, she used this distribution to compute building heights. So how do you know this? How do you do this? You can, I think, look at the data. Based on the data, empirically, she found that in urban setting, again there is a difference. That's where you have to do a lot of literature. The question was, our collaborator asked, put some buildings at different heights, but you want to know how should I design put the height? How do I choose? So one is you can put randomly. The other option is look at a good reference and see She said this is the probability density for heights. That means if you, how do they do? From a statistical sense, you go to, for example, Warangal and some center of the city, and then look at the find out that you can't do on your own. There will be some data available. So what are the heights of different buildings? And then from there you can come up with your distribution, and this is the distribution she showed. Okay, so now use this distribution to pick some random samples. See, sometimes you can make the problem more interesting, by doing some studies. So that's how these numbers are coming. These are not totally random. They are random numbers, but they're not totally random. She didn't make it up. She uses a distribution to pick the numbers. Yeah, if the height, if the what you're saying is, depending on the height, you see the reflected component. The lower the height, probably you'll get longer paths. Yeah. Here are the same things that we already learned. Free space path loss, and that will be the baseline. Free space path loss is the baseline. This for the free space path loss applicable to line of sight. Obviously, this is nothing new, clearly. So what you are saying here is, this is the free space path loss. So from what's the distance between transmitter and receiver, and you are plotting the path loss. And this is for non-line of sight. This is for both, of course, they have to match. Then they are matching. Even the tool also has some physics model to build the simulation. So this has to match, like free space path loss and line of sight will be the same. So what happened here? She actually did a bunch of experiments. If the transmitter and receiver are the same height is 800 meters. Yeah, she actually went up to 800 meters, I think, totally. Okay, ignore that. Basically, height is constant. This height is constant, but then distance between transmitter and receiver is varying from 1 kilometer to 3 kilometers. And then she obtained, through the simulation, she got all those line of sight and non-line of sight components, and then this is the average. You get a lot of non-line of sight, but only one line of sight, and obviously these two have to match. Make sense? At least reasonable, right? You may not be able to understand everything, but reasonably, at least to some extent, how she's only plotting the path loss related to line of sight and whole lot of non-line of sight. And these are the expressions for delay spread. Received power, actually, in this case, even though she didn't mention it, is the received power of each path. Because transmit power is always the same. There is only one signal, one sinusoidal signal that is sent. The received power varies. Transmit power doesn't vary. Okay, time of arrival. So TP, P sub P is the received power for n paths, and TP is the time of arrival. Each non-line of sight will be received at different times, and then she computing mean arrival time, and here is the RMS delay spread. We learned about delay spread before. We have learned about RMS delay spread. Here is practically we are measuring. Okay, now it makes sense, right? If I showed this in the first slide or first talk, you won't understand what we are talking about. That's the reason I covered the basics first. And then you can see, look at this, at different altitudes, she went all the way from altitudes of what? Altitudes of the transmitter and receiver. They're exactly the same height. She didn't change the heights of transmitter and receiver. But this, you have to start with a simple model first, and then RMS delay spread is reducing. So the question comes, where is this? Normally supposed to be like monotonously decreasing. So when you see something like this, you have to ask. We have to ask her, or the researcher has to. Why is this? Why is this? So potentially, probably we are. Our reasoning is, you can't throw it out and say it's random. No, there is a reason why is this, because you're doing averages. there's something called law of large numbers. The more experiments you do, you're supposed to get a good distribution. So in fact, yeah, so point is this number is coming because there are obstacles in the air at some heights. So it's something to do with the obstacle that she introduced. So what we are going to do going forward is just remove all the obstacles in the air, see how it works, and then I asked my collaborator, should we even consider we considered obstacles. So he was expecting, he was not thinking about adding these obstacles in the airspace. But when I mentioned, okay, this potentially we want to, potentially you will see some other aircraft, some other obstacles. So you cannot not assume, you cannot drop them from the simulations. So he said agreed. He agreed, and then we are working on that now. So what she is saying is, at some point it will be zero, meaning that, what do you mean by that? When you say RMS delay, at some point the power is going to be zero. What does it mean? It means that you're only getting line of sight, nothing else. Where the delay comes when you are seeing non-line of sight. So when, yeah. So there are some, these also supposed to be like kind of a monotonously decreasing, and we are getting these ups and downs because of the obstacles. That's our guess. We don't know yet. So as I said, it's still in work in progress. So if you change the building heights, then you get a different result. If you change the building materials, you're going to see a different height. If you change the building material, you're going to see different results. So we want to collect all this, and then look at all these results we got. And ultimately, the goal is to use these experimental results to build a theoretical model. Okay, we are still working on it. Okay, so I think I'll stop here. She did a lot of experiments. And if you use directional antenna, what happens? And if you think about all these options are there in the tool, so but we have to come up with a little more details about the antenna parameters. If it's a directional antenna, then you have to set up all these parameters. MIMO. If you use multiple antennas, then okay. So basically, this research is about this presentation or this lecture is about how do we develop a empirical air-to-air channel model. And the key things are understanding delay spread, power delay profile, path loss, and then those are the key things that we need to understand conceptually, theoretically, and also practically. Then I think we can develop such models. All right, I'll stop here. Any questions before we wrap up for today's lecture? Mm-hmm.
So even if the buildings are of the same material, the surface, like the roughness of the surface would either reflect or scatter the signal.
That's also there, yeah. That's also there. You remember the scattering that we talked about. It depends on the. It's difficult to capture all the finer phenomena, So in general, in this case, we're only considering the reflections only. So it's not considered. And one thing is probably, yeah, the question you'd ask is, what happens after scattering? Are you receiving the scattered signal back to the receiver? In this case, probably it's not. So you can ignore in that sense. So first of all, understanding all these different physics aspects is important. But then see what are applicable for this. Okay, if the scattered signal is going to travel that long, then you have to model that. But notice that since we don't know what exactly are the buildings and building materials, and all those things are only some high level assumptions. So it is sufficient to capture the significant things and ignore the. But even you model, then there's something called overfitting, and you try to overfit, then it doesn't generalize. In machine learning, there is that we use the term overfitting. Don't try to, if you don't, we shouldn't try to overfit for one particular data, but if you do that, it will fail in other cases. But the good point, you're right, that it is true. The surface characteristics will also affect, but given that reflected path is, the scattered component is not going all the way to the airplane, we are okay to drop it. But a very good point. Anything else? Oh, well, for now, so remember, the fact that you are trying to looking at drone to drone communication, you're only looking at line of sight. Okay, line of sight is because of reflections, but it's not about going beyond visual line of sight. We're only looking at like a simple scenario, like I'm using this door because I don't want laser light to go to your eyes. So you're assuming that there is one vehicle here and there is one vehicle here. Okay, the distance that is should be reasonable enough to reasonable enough in the context of one single hop. Okay, the distance is changed. If you change the distance, if you vary the distance from 100 meters to 2 kilometers, what does it mean? You are looking at a scenario where the communication range is varying from 100 meters to 1 kilometer or 2 kilometers. So in fact, that's another thing one of my collaborators mentioned. We wanted a model where you can change the communication range. But to answer your question, we are saying that we are saying that it's only one line of sight, just one link, one communication link. That's it. Yeah, if you can increase the one hop distance, that depends on the transmit power. Okay, for example, if you in one experiment, we're trying to see, how come the range is so small? All we had to do is increase the power. So, but of course, it has to be within the regulations. I'm not sure whether we. Yeah.
Whereas if you take directional network, even a force, light force, it scatters exercise, and that is subject to enter into your.
So look at these papers. This is the this is the paper I was talking about. This paper got very well recognized. We got a lot of people actually used it. Air to ground propagation channel. That's exactly I'm trying to work with him to come to build this air to air channel. And then look at, there is one paper, air to air channel. There are some effort, but these are assuming you're only looking at 100 feet or 200 feet. Yeah. This is my lab. Where is this? Here. From North Carolina State University. Yeah, he graduated from Florida. You know him? Who? Okay, yeah, he's from here. He is well known. Yeah, he wrote lots of papers actually. Georgia Tech. Yeah. But the nice thing is they're all kind of new area. That's fun to work in a new area. But at the same time, you have to be careful. If you do well, papers will be read. Otherwise, say if you don't do good job, nobody cares for it. They're put in the dustbin. But so we have to do a good job. At the same time, make sure that it's consistent with the known results and all that. It takes some time. Okay? All right, wonderful. Have a wonderful rest of the day. So we are done for this. So, yeah, yep, we're done for. Yeah.
Hello. Hello. Okay. Good afternoon. Today we'll be looking into some details on machine learning applied to communication systems. And basically, if we try to look at this topic very carefully, most of the communications what we are dealing right now, whether it is line or wireless, the next generation communication systems are heavily filled with machine learning algorithms. And why we are trying to do that is the data coming into the system is very heavy. Like for example, if you think like 50 billion devices are sending data to a server for compile or to the cloud to compile it, it is not a small thing. And it is not possible for a small routines to run and check the data or not. And hence we move towards a machine handling the data sets. We are giving the data sets to machine to handle it and provide the information to us. For example, if you try to look into a fire sensors in the house, if a fire accident house, the data has to be picked up by the fire station and they have to report at the place and put off the fire. That's the scenario if you try to take, that every 5 minutes or 10 minutes, the time is sufficient for the damage to be caused by the fire. So every second they are trying to send the data, and that data the fire station has to check whether is there any fire or not, indicator or not, and discard that and take a new set every second and check all the data and throw it off and take the next set until they find some discrepancy and then try to look into it. And it is not possible by a human being because the data sets are so large and it cannot be handled by a human. It has to be handled by a machine. Hence, the data sets are very large, right? And if we try to look into the 6G communication, what we are trying to do, every segment is filled with machine learning. Every part of the communication system is provided with machine learning, right? Whether it is a receiver synchronization, it is there. Or channel estimation, machine learning is there. Equalization, ML is there. Symbol demapping, ML is there. Decoding, ML is there. Or if you look at transmitter, encoding, ML is there. Symbol mapping, ML is there. And modulation, ML is. Which means that every block in the communication systems are loaded with machine learning algorithms. And it is the order of the day that if we say that we are not into it, it means that you can see the questions over here, right? So if you take the classical 5G systems and if you are running into a 6G, it is heavily loaded with machine learning or deep learning algorithms, which will be handling it because the user densities are increasing, the information bits are increasing. Because when we try to move towards the 6G, the data rates are at terahertz and terabits per second or pentabits per second. It is no more megabits or gigabits, right? 10 to the power of 12, 10 to the power of 14, 10 to the power of 16. We are trying to reach that so many data bits are coming into the exchange and they have to process it. Either it is a mobile center or some center. It will come into that and they have to handle it and service the things at that speeds, right? So, no, sorry, machine learning. The machine learning is we are training the machine to handle such type of data. Sorry? No, the machine learning, we are giving it intelligence to handle such data. So the intelligence might be updated every day. Like for example, I'll tell you a simple example. So when we are in the first class, we are only taught 2 plus 2, 3 plus 3, 4 plus 4, single digit numbers. When we move to second class, we have been taught with 2-bit addition, 2-bit multiplication, 2-bit subtraction. And as we go on, when we come to plus 2 or plus 1, 11 and 12, we are taught integration, differentiation. And as we go along, we get number of mathematics involved in it. So like machine learning also, initially we train with a subset. And then as and when the demand comes, we increase the data sets to that, increase more and more power into the system so that they can do the job more efficiently, right? It is only a training set. If I know what is 2 plus 2, I can easily see if a number is there and given some addition or subtract, I can do it. So it is like a neurons which you are trying to train it and keep it so that when the data comes, it tries to look into the data and predict it. So these algorithms are, again, we have different types of algorithms which we have to look. So they are basically mathematical algorithms only, right? Am I clear? No, we write a code and keep it to the machine so that it executes. So like when we write a C code program, we say that this is the input and this is the corresponding result what we get. So the result, the input what you're giving, you're typing some numbers or some file name or something, image or something, and you get the result out of it. So the machine learning also, we train the machine with some code, and we give the input data and ask for the result. So we have a lab session after this class where we give you some training on popular machine learning algorithms. We have 5 or 6 algorithms. I think 5 algorithms or 3 algorithms. We train you with 3 algorithms. Rest, I think you can easily do it. Once you are trained with 2 or 3, then rest of the algorithms you can do it. So we'll write a code for 3 algorithms. We run it, and we train the algorithm with some data set, and we'll ask them, if this data comes, what is the outcome, right? After this class, we'll try to do the lab session on that, okay? So when we try to look from the data point of view, so if we assume that today we have $80 billion 80 billion devices connected to the network, or 50 billion devices are connected, and next 2 years we might get 80 billion. So you can see that the data, what it is coming, everywhere you'll see data on zeros and ones only, right? And so much data is unable to be done by your laptop or your desktop and all. We need a huge memory for holding it and then do processing on it, right? So you see the complexity of the problem. It is, for time being, what we try to do is, since we are seeing one drone, we might not have so many. But if multiple drones are coming up, multiple HAPs are coming up, multiple balloons are coming up, multiple LEO satellites are coming up, and apart from that, people are trying to use some pseudo satellites, like everybody can keep a small satellite and communicate. So when we are getting so many devices into the network, along with the existing devices, what are there on the terrestrial network, the number of bits which are moving to the cloud or handling it is very difficult, right? So under that scenario, what we try to do is, we try to do some analytics on top of it and take the information what is required and remove all the bits, right? See, for example, you take a good example is a JEE exam. There might be 2 lakhs people who might be writing, you are selecting some 10,000 or 20,000. Similarly, what we try to do is, from the whole set of data, we try to extract the data which has information, and we reject the data which doesn't have information. So we call it as analytics. First step is we do analytics on the data. On the huge data, we call it as big data analytics. And we try to get the information out of it. So what we do, we first examine the raw data. First step is you see what are the data available to us, what is the data coming into the system, and then we draw some conclusion. Okay, this data is useful, this is not useful, this is useful, this is not useful. We try to draw some conclusion on it, which means that we should know what is important to us. See, the data, what is important to us, might not be useful to you, right? So based on your, because the data is so huge, there might be a lot of information in it. I might be looking for only temperature. Somebody might be looking for humidity. Somebody might be looking for some other part, and so on. So you examine the data and pick up what is required. So based on that, you draw a conclusion. This type of data is useful for me, right? And then there is what we call it as lake and stream. This is of prime importance because lake and stream will tell us whether we want to store the information or just look at it on the live data and say whether it is required or not. So lake means you put it in a pond type of thing. You keep it in a pond, store it, and do processing out. Stream means live data streaming. So data is coming on, in that data you pick up whatever you want. So what we do is we segregate or we try to either store it or use live data and stream it out. Okay, most of the cases live streaming is sufficient. For example, you are monitoring a place by a camera. So you get live stream of data and you don't need it. You want to know when there is an event occurs, right? So there should be some machine which says that, okay, now the event has occurred. It will be keep on watching it as and when some event occurs, it only tells us, and then we capture the data, right? Like some police, he is standing there observing the traffic. When now something is going wrong, he'll go and act, right? The other one is you keep the data set and look it afterwards, called as a lake. So we have a data lake corresponds to a huge storage. You need a lot of storage over there. You need a big memory, cloud memories or something you try to use because the data is coming in. You have to use it for storing purpose. So that is one important thing. And when we store it, we have a lot of information. We have historic information because you have stored it. You know yesterday what happened, day before yesterday what happened, and previous day what happened, and so on. Because you have the data. For example, if you try to see the weather over a year, last year by this time the temperature was 24 degrees, so I can predict, so tomorrow the temperature might be 27, right? So the historical data is available to us. Based on that, we can estimate what can be tomorrow and so on, right? And the next thing is you can do the job at ease. It is not that you have tied up with time. So once the data is there, I can use it for a lot of applications like predicting a linear regression. I can draw a line to what can be tomorrow or what can be, all these things, predictions can be done on the historical data. Whereas the data stream, it is a live data. Live streaming is coming in. So you cannot really say that prediction is easy, right? But for handling the live streaming, you need start going to vanish. It will be there for some time. I can do a lot of things. Whereas real data, it vanishes. It will not have, it will be there after some time to do some analytic on top. You need to do much faster where you have to use parallelly, you have to do things at set it out, right? So this is for storage, long-term historical data, easy to use. And whereas if you try to see the data streaming, real-time data, parallel analysis, and difficult to handle it, right? So in most of the cases, what we try to do is we do clustering. Clustering is an easy job for us. For example, you have a big sentence. I can bring all capital letters to one side and small letters. That is what grouping is. Clustering is nothing but grouping, okay? It might be useful, it might not be useful, different thing. The example of clustering is you bring all one type of data to one set and other type to other set and so on, so that you can segregate it and people whoever wants it, that group can use it. Or suppose, for example, consonants and vowels. Vowels, you can take it and so in a line, how many vowels are there or consonants are there, you can take. That is one example of clustering, grouping all of same feather at one place, right? Or you can see, I want in a paper you have written, I want to find how many two letter alphabets words are there, or 3 alphabet words are there, or total words how many are there, I can analyze it, right? So based on that also I can get some information. because I can say evenly the votes are distributed, or you are trying to use only one set of votes for your paper, how many times it has been repeated in your paper. I can analyze everything, right? It gives me some type of information if I am trying to look into that, right? So the clustering is one of the good example of finding a group from the other groups, right? And most of the cases when we have large data, we try to use clusters. We bring all one type of data to one set, other type of data to one set, and so on, so that it is easy for us to handle it and remove the other groups which I am not interested in. So this is a good example of a clustering. I have students of NIT, and of that, I try to find out who belong to the same state, like how many of them are from Andhra Pradesh, how many of them from Telangana, how many of them are from Karnataka, how many from Tamil Nadu and all. From the largest set, I am trying to find out, and from that state, I can find out how many are interested in software tools, so that I can get the information, right? So now I have a full-fledged information of the data available. So this is only an example, but you can apply to anything from the drones and all. Lot of communication is coming. I can segregate the data which is coming from drone, which is coming from household, which is coming from mobile, which is coming from lands, and so on. I can segregate them, so that I can only look at aerial drones data, not other data, because that doesn't belong to me, right? So first you have to pick up a group or a cluster of the data what you're trying to look at from the complete data pool, right? And that you have to do, you don't have a liberty to do whenever you want it, because the data is coming in live, and whether how much memory you have to store it, for how long you can store it, and from that time you have to pull out your interest, okay? And these are all, like, if you try to look from the practicality there, you hardly have time to do that, right? Because the live data are coming in heavily, and your RAM or memory or something is getting filled up. Once it is filled up, when the next data comes, the first data has to go out. When the second data set is coming, the second data set has to go out, right? Because your capacity is that much only. You don't have, like, for example, you have a jug of water. If you remove one glass of water, you can pour one glass of water, right? If you don't remove it, another glass will be spilled over. The new data will be spilled over. You don't have the information about it, right? So the discharge and the coming in has to match for you to have some time on doing the processing, right? So this is one important thing which you have to keep in mind. Try to find out you do some segregation so that you pick up your information, and you can store that information. Rest of things you can empty it, so that you have space for the new incoming data sets. So now, when the data is coming, the data can be of different types. It can be either a structured data, or it can be unstructured. What is the structured and unstructured data? For example, when you join your college, there might be a form which you have to fill up in the online, which is name, roll number, your date of birth, or your program, or your male or female. There is a set which you have to fill it up, right? That is what we call it as structured data. There are fields are structured, they are being written very clearly, and you have to put those data only, right? In the date of birth, you cannot write some words. You have to be some numbers. In your name, there is some 20 alphabets you can put in. You cannot write a sentence over there, right? So everything is structured over there. So if you try to look the data when you keep it, it goes into a database, right? Each user will, or each student will put the data, it goes into a database. And the database, what we are trying to look is a structured database. It has number of columns are same for every student, right? In a database, if you try to open it in an Excel sheet and see the name, place, and the date of birth, and the gender and all, they are well written in a column wise. It will be appearing in your Excel sheet. That is what we call it as structured data, right? Unstructured is, you don't have anything like structure and all. You can put your photograph, you can put your signature, you can put your name, wherever you want and you can send it. And if you open an Excel sheet, you will not find anything. You will not be able to sort it out also. I want to sort out by date of birth, I will not be able to do because there is no column indicating date of birth. Right? So there is an unstructured way of writing it and a structured way. So when you go to the structured and unstructured ways, we have a lot of problems in that case, where in structured you have a RDBMS software or something like that, where you can have the data written very well into the database. Right? If you are good in database structures and all, you have a rational database management system, RDBMS we call it. So you can open the RDBMS, everything will be in a structured format in it. Right? So these type of RDBMS and all is not suitable for storing the unstructured data. Right? We need a different type of database to handle such type of thing. And one good example is MongoDB. You heard about MongoDB? So MongoDB is one database where you can use it for unstructured database. Okay, the unstructured can be text, audio, video, photograph, image, whatever it is. Right? I hope it is good up till here. Lot of data is coming, and from that data we are trying to pick up what is clustering it into whatever format we want, and we can use it as a real-time or data lake. We can keep it in a lake and remove it whenever we want, or we can process online and send it out also, right? And this data can be either in a structured way or unstructured way. In a structured way, the formats are fixed, and the rational databases are good enough to handle that. When it comes to unstructured, there is no fixed one. Data is variable. Text, it can be image, it can be video, it can be a music, whatever it is. And any format it can take, and anywhere it can sit. So what are the sources of unstructured data? If you try to look into the internet, there are billions of bits content shared on WhatsApp. So what you will write? Some people will write, hello, how are you? Some people write, doing good. Some people write, hi. Right? For same message, you have different ways to express. Somebody says, hello, Mr. Sai Prakash. Some will say, hi, Sai. Some will say, cool, Sai. So there are different ways, right? Because the text, what we try to use in the social media platforms have changed the structured format. People use codes, people use emojis, people use a lot of stuff, right? It is not one way of telling. See, people write namaskar, but now symbol has come up. People put this one, they will not write namaskar also, right? So there, it can be an image, it can be a picture, or it can be a word, text, or a whatever it is, they have their own way of doing it. Some will put GIF files. I think you know GIF files, right? There'll be continuously a little bit motion in it. Okay, so the namaskar will be swinging like this. Okay, so the data what we are trying to look from the internet has no structure, right? So majority of the things, if you try to see, the social media platforms like Facebook, Twitter, WhatsApp, a lot of things have come, X platform and all. People have their own language in representing it. They have the same thing they can represent it in text, same thing in image, same thing in video, same thing in GIF file, whatever it is, they can able to do it. And know how to store them into a database and retrieve them whenever we want, right? So we have to move towards a non-structural databases and try to look into that, right? So this is about the text. So don't assume that text is the structured language. Earlier it was, but now it is not. Because whenever we say text, this is the best thing, we can handle it, right? That is there with a lot of people impression. Text means, oh, now I can handle it easily. But it is not that easy, because you have to capture the emotion of the text and then analyze it, right? So now we have to dig it, right? The text, we have to dig it and see whether it is good or bad. For example, you have somebody will express some news in the Twitter, and then you will see that people put comments, going on putting comments, 1,000 comments, 2,000 comments, 3,000 comments, and so on. So now, if you try to look at, there are positive and negative words. Some people try to praise it, some people like to abuse it, right? That's what we see generally when a tweet comes. We'll see whether it is a positive or a negative, right? Some people say that, yeah, very good, thumbs up and all these things. Some people will put thumbs down and start using language with different languages. So there is a positivity in it, negativity in it. And now, if you want to see what is the outcome of that, we have to use a sentiment score, how many positive is there, how many negative is there, and difference of that will tell us whether it is a good tweet or a bad, right? 1 and 1 will not tell you whether it is good or bad. So if it is greater than 0, it is a positive. If it is less than 0, it is a negative. And if it is equal, it is a neutral bit. That's how, if you give it to a machine, it calculates it and tells us. Because it is not possible for us to go through all the 2,000, because nowadays people are running in lakhs, not even thousands, right? For everything, it comes like 10,000 tweets or 50,000 tweets and all. So it's not quite easy to fill up all those things and see how it is and all. We have to generate a algorithm so that it manages and tell, okay, this is the score and this is the score. You might have seen on the TV screen saying that positive this much, negative this much and all, right? Because they don't have time to read all the 50,000, 60,000 tweets what they got. So there is a code which runs on it and say, okay, this is positive, this is negative, up and down it will be swinging. Right? I think you might have seen the scores, right? So that will tell you how these things are, opinions and all. So why we have to do this? That's the question, right? Why we have to do all these things and all. This is not so much important to these fake news and all, but for the communication networks, it is a primarily job. We have to dig it out and find out, because we have to make a decision on top of it. Right? It is not like knowing it and leaving it. We have to do some corrective measures or decision on top of it so that the system runs smoothly, right? Otherwise, the drone, if it doesn't get an instruction within a well-defined time, it doesn't know what to do, right? Or if it doesn't control it, it might hit some other drone. So there is a very possibility that the drones have to be controlled very carefully, and the information has to be given to the drones in the appropriate time with a minimum latency, so that they all follow into one stream. So now we have to extract information from the data lake. When the data is coming and falling into the lake, we have to get the information as fast as possible, because the lake will get filled up and it will be overflowing it, right? So now the algorithms what we are trying to look at has to do this job, right? So now the data coming from various devices, whether it is a drone or it is from a base station or it is from a mobile or whatever it is a data. That is Internet of Thing, the mobile is a thing, drone is a thing, everything which has the internet connectivity, right? A network connectivity. So when it is just data is coming in, it is not for curiosity we are trying to look at. It might be curious to look at, but every time we have to handle it correctly so that we can have a positive result on it. Okay, we should not handle it in a different way and land up with a wrong result, right? Because as we are trying to look from the point of view, for example, if you take a jumbo aeroplane, there will be around more than 10,000 sensors working on it. Okay, so if you are trying from that end and the number of text what you are trying to look at is more than tens of thousands, and that data is coming in, so I have to prioritize on data which I have to look immediately, and some can be delayed, right? For example, I have to continuously see the turbines are moving properly, and there is a engine temperatures are maintained properly, and there is the speed of the plane is maintained properly. All these things have to be monitored prior to the passenger request for some music or something. He might be interested in some movie, he might put it, and that not be prioritized, right? There are some things which have to be prioritized, like the engine and so on, so that in case if something happen, I have to react to it, whereas here it can be delayed by few minutes or something like that. So this is prime important. The data might be curious only. From that, I have to find out the levels of priority and allocate the resources for that. Okay. So now, if you try to look at the traditional management systems, what we have, they are not ready for it, and we need something, a different type of databases to look into that. As I told you, mostly nowadays unstructured type of database we are trying to use. So as I told you, all the data is not same. They have to be categorized. They have to be separated. I have interest in some type of data. Someone is interested in some other data and so on. For example, I am trying to do the drone flight control. I need only that much. And he is interested in drone internal part management. He is only interested in the internal part temperature management. And you are interested only into what is the temperature of the drone when it is flying. You will take that much only, right? And he is interested only to know whether it is moving in the right direction or not. He will know that. So each one have their own thing to search it out from the maximum data. So that we have to do some type of categorization and then try to move it. And we have now two important things. The data, what we are trying to get, it can be something like in motion or in rest, right? So for example, when you are trying to monitor some area by a drone, then you cannot say that camera can be switched on after 1 minute. It has to be continuously on. Whereas when I am trying to find out the humidity at a location, and if I want to monitor it after some distance, I can monitor humidity again. I need not have to monitor humidity continuously. Because even if I monitor like this place and that place, I know there will not be much change. Temperature, it will not be much change. For 100 meters, the temperature change will not be that much, right? The humidity might not change, might not be that much. So every 100 meters, I can start measuring the temperature and humidity, whereas video, I have to keep it on to get a live data what is happening within the 100 meters also, right? So there are some data sets which are typically important, which can be periodic. Some things might be non-periodic also, and so on. So you can categorize it like that, and you can take it. So now when we come to the drones generate both structured and unstructured data also. It is not that the drones are only structured data. We have both types of data available in the drones. So when we have that, you please remember that the structured data is easy to analyze. For example, I have a student database. It is easy to find out how many are born in year 1990. I can just put a command and it gives me the total list. Or if I want to find out how many boys and how many girls, with one command I can get it, right? If I want to find out how many people are there from this state, I can easily find it. Because they're all lying in a structured format. Only thing is one command is sufficient to search one column. I need not have to search the complete file, right? But in case of unstructured, it needs some type of mathematics or analytics or some type of language to, or some type of intelligence to find out all photographs, all the signatures, all names written in different hand styles and all, and then to it. It is not that easy, right? So now the problem of that is we'll handle all the non-structured data using machine learning, right? And coming to the communication system, if you try to see, with the communication network in place, for example, you have a terrestrial network. We call terrestrial networks where On the ground, all the networks are integrated. And right now we have internet as a good example of that. And now we have drones network, where it is, let us assume that it is a totally new network. We have not connected to ground. There is a separate network running parallelly, and they connect to internet. There is a separate network like satellites. They are connected separately to ground station. They are separate. And if the ground station and the base station are connected, then there is interconnected. Let us assume that they are separate networks. And now each network has their own requirements. For example, you take drone network, they need some type of bandwidth for communicating among the drones. If you take satellite, they have a different type of communication requirement for the, see, satellite to satellite communications and all, they need few kilobytes of data is sufficient to communicate. Whereas if you take a terrestrial network, we need tens of MBs to connect. You are not happy with 1 MB, 2 MB, you will need 10 MB or 20 MB to communicate. And satellite, it is not like that. They are not watching movies, right? Whereas you are watching movie. So you need a high data rate, bandwidth for you. But the satellites are not interested in watching movies or watching some WhatsApp. They don't talk on WhatsApp or not, right? They have a different requirement totally. And similarly, drones, they have a different requirement based on the application. So when we have a different requirements for the different networks, and if you're trying to tie all these things, there should be a mechanism to allocate whatever they want, right? There should be some mechanism where if you ask some sweet, I have to give it. If you ask some mixture, I have to give it. If you ask something else, I have to give it, and so on. Okay? So I have an intelligence. So I know looking at him, he needs sweet. And he needs some type of mixture or something. And he needs something else. He needs some rice. And I know that he needs the idli. So it is there in my mind, so I can use it. So now we are training something like that and keeping it live, so that when a request comes, it says, okay, you take this, you take this, you take. So this is the process what we are trying to look at. We are trying to train a system with some mechanism so that it can predict what the other wants it. So that's what we are trying to look from the communication point of view. We are trying to make a machine learning algorithm for the communication purpose. Based on the parameters, we allocate the requirements like, okay, terrestrial network, they need higher bandwidth. Whereas drone network, they need lower latency. Satellite network needs latency is very large for them. So they are not power, they are only looking at power as a requirement because they have to be charged by solar system. And the sun will be there only for 12 hours or something like that, right? So there, each network have their own requirements. And based on that, this machine which has been trained has to allocate the requirements of them, right? So now we try to come up with those solutions. And now when we have that, the data has to be classified either it is in transit or it is in store, right? So when you are trying to allocate the resource, and if the resource is not sufficient to get the live data, then it is of no use, right? So most of these algorithms, what we try to do is we try to use fair distribution. I want everybody to get a share. So for example, let us take a good example of that. I have 150 kilobytes of resource with me, and for a voice call, I need 64 kbps, right? So there are 6 people, so 3 voice calls are possible, but I don't have a resource. I have only 150, and each one requires 64. So the total will be 128 is the maximum. So if I now do the equal distribution, like if I have 150 divided by 6, if I give them, none of you will be able to talk, right? So the question of fair distribution or some weighted distributions are easy to say and implement, but intelligence is not there, right? So if an intelligent algorithm is there, I will see that at least some of the bandwidth is used carefully instead of wasting it. Okay, so I'll pick up which 2 I have to give it. Out of the 3, I can give only 2 calls. So I have to make a decision which one is important, prioritize, and for them I have to allocate it. For the least prior call, I can say wait until this is complete, I can transfer. Right? So building up intelligence is a prime job of any machine learning algorithm. So when we are trying to look from the machine learning algorithm, data is given, the data, the results what we can get is descriptive, or it can be diagnostic, or it can be okay, descriptive, diagnostic, predictive, or prescriptive. So the first one is descriptive. What does it say? What it happens, what is happening, it can tell you, right? Or either the data is presently happening, or it has happened, or it is going to happen, right? The description can say that, okay, it is happening now, or it has happened yesterday, or it will happen tomorrow. That much I can say from the data what I got. That is what descriptive. Diagnostic is see, when you go to a doctor, right, you describe, I am having this type of problem and all, then he'll say you go through this test, you diagnose and come back, seeing the results, he says, okay, this can be happening, or this has happened and all, and he give prescription for that. Sorry? Why? So the diagnostics is a way to look into the data carefully and try to find out, okay, diagnostics, as he said, it is a why, question is why, and to find out deeper into it, why, what had caused actually to happen, right? And then predictive is, we can say, based on the past history, this will come out like this, or this might happen. It is not that it is going to happen. It can happen. Like I told you, we have a historical data for last 10 years. 10 years on March 10th, the temperature is this much, so tomorrow it can be this much, right? So the doctor has an experience like, okay, this type of symptoms I have seen in these cases, so he says that, right? And then comes the prescriptive, like what should be taken care so that the things will not go bad. Okay, so these are the 4 types of results when we try to use the data analytics on the data what we are trying to get. So it can be of either of a descriptive nature, or of diagnostic nature, or it can be a predictive nature, or it can be prescriptive nature. So now the machine learning. So before going to machine learning, let me just give you an overview of some of the terminologies which are popularly used in the machine learning. So we have the machine learning is, we are artificially creating some knowledge to the machine. So this comes under a broader class of artificial intelligence, right? We have a broader description of what we call it as artificial intelligence, or knowledge-based systems and all. So out of that, we are trying to look only to the extent where this artificial intelligence can be given to machine. Okay, we are only trying to look into a subset of artificial intelligence where we can apply that directly to machine, and machine can do some jobs. So most of the machines to machine communications, we use this type of information or intelligence. And if we want to know much deeper into it, we have deep learning into it. Okay. To know finer details and more into that system, we get into deep learning, right? So you don't get confused between deep learning, machine learning, artificial intelligence. They are all subsets only. Okay. If you take a bigger set, subset is ML, and from that subset, still smaller subset is DL, and natural language, NL, NN, and all these things will come in. Okay, so we are not confused with these words, whether you can loosely use ML, DL, AI, and all, as far as you know the difference between them, right? So now, when we are trying to look from this point of view, machine learning from the communication point of view, we want to make more sense from the data what we got. We want more information from the data what we are getting. From the drone, if we are getting it, we should know what is the position of the drone, what is the velocity of the drone, which direction it is moving, what can be the next move of the drone, whether the fans of the drone are moving properly or not, whether there is any problem with the heat of the drone, or whether its job is to scan something image, whether the camera is working good or not. This information we want it. So from those information, I am trying to look into the flight control, moving the drone from one end. I have to pick up that data set from it. The other people will pick up their own, like fans are moving properly or not. Some pilot will be there, he'll be looking after those things, right? So there is a track engineer who will be looking after track. There is a pilot who will be trying to increase the speed and decrease the speed of the drone to go up into the required altitude. Otherwise, it might come down, it may move up and all, or it might be moving away from the track. So these are all the things we have to do it. So there are different clusters coming up of that. And we have to see from the data set whether it is proper or not. The data what is generated is good or bad, we have to decide. So there might be 4 fans which are moving and 3 are moving and 1 is not moving. Automatically it has to be picked up from the cluster what it is, right? So we need some efficient tools and algorithm to find out data more information. From the data, we have to somehow extract a lot of information from that. So now, if you try to look from a bigger picture, ML is a subgroup of AI, okay? It is a subset, we call it a subset of AI. And it is concerned with any process where the computer needs to receive a set of data that is processed to help perform a task more efficiently, okay? Because what happens with human beings, after looking for some time, we loses the information. And whatever data comes, we'll assume that it is same, right? But the machine cannot have such type of lags and leads where a human being might be having it, right? So we want the ML to be processed such that there should be some process which is trying to process the information and get the information out of it, right? And it should be more efficient. So we have 2 categories of that. One is supervised learning and other is unsupervised learning. Any questions? So we group the machine learning into 2 parts. One is supervised and other is unsupervised. There are other groupings also. Let us stop over there because there are a lot of groups coming up nowadays, like hybrid groups and all these things. So in supervised learning, if you try to see, the machine is trained with input to which there is a known correct answer. For example, when you are small, we'll say that read 2 into 1 is 2, 2 into 2 is 4, 2 into 3 is 6, 10 times or 20 times or 30 times, until when I show 2 into 2, you will say 2 into 2 is 4, right? That is what training is. Training is you go on giving the same data until it gives the correct answer. Then you say the machine is ready and trained. And now if you give an input, it says this is out, okay? So the primary job in supervised learning is to take a stick, sit with the child, read until it gets it, and then now you can say that it is perfect, it can do the job, right? And supervised learning is efficient if we have a large training set. If the training set is larger, instead of 10 times, 20 times we make it you read. 30 times you will not make a mistake, right? So if the data sets are large, right? If you have a larger data set, the machine will get used to the data sets, and then when you give a new data, it can predict more accurately, right? The accuracy depends on how much data set you have trained the machine for that, okay? So most of the cases we'll say 80% data set and 20% actual data and all. If it is 90-10, you get more accuracy, right? If you say 95 and 5, still more accuracy. If you reduce it to 70, you can see the accuracy decreases. If you bring it to 50-50, still the accuracy goes bad, right? So always the data set has to be given 100% to the machine, so that whenever you give a data, it will say right answer. Your outcome accuracy will be 100%, right? It is not that the algorithm is giving you efficiency. You have trained the algorithm such a way to give accuracy. Okay, so I have seen most of the people saying that I am getting accuracy of 99, 98, 97 and all. They think that they have done very good in machine learning algorithms and all. It is not the accuracy of that. Because of 80% you are getting that. If you reduce that to 70 and 30, you will not get that accuracy, right? So please remember that the outcome, if they say that I have 90% efficiency outcome and all, it is because you have trained the machine so good that it is able to predict it properly. Okay, so your analysis has to be in that direction. Regression is another way training the machine with measure values so that the machine can predict the outcomes properly. So if you have some past history of it, train the data with it, like last 10 days it happened like that, tomorrow it can happen like that. Last 1,000 days it happened like that, it can predict more accurately. So you are fitting a regression over there, linear regression or some type of regression, so that the outcome will be predicted properly. So this is the main thing of machine learning. Machine learning is you make the machine learn as much as information you have, so that it can. For example, let me tell you one thing. Suppose I have trained the machine with my data. Like every day I come at 9, go at 5:30, I teach something and I do some job and go. So it knows my data perfectly. So tomorrow if I ask him at this time what I'll do, it says that tomorrow there is no class at this time, you will do some office work or something. But if I go out to a hospital, it doesn't know that I go hospital at that time, it predict wrong. And that's how you can see the Google Maps and all. It says that you take this route and you'll end up in sea or somewhere, right? Because that point is not trained to the Google Map content, right? If that point has been trained perfectly, it will not lead to that point. There are a lot of points in the map which have been not identified yet. See, most of the cases when you map, they'll say that you insert your data over there, but generally we don't do it, right? If you train that one, automatically it goes to the same place. If we don't know the information, even though you're trained, it goes to the closest one and says this is the point, right? With some accuracy it has predicted. It is not 100%, right? So now, unsupervised. This is a very good example. Like when you try to look from the unsupervised machine learning, you are not going to train the machine with that. We are trying to look at small deviations in multiple dimensions, right? What is the change yesterday and today? What is the change on January 1st and January 2nd? So you try to look for the changes what is occurred. It is not that you have trained something and you are trying to predict. You are trying to look for the deviations in multiple dimensions, and then you are obtaining after computing some iterations and all, you conclude with some answer. And this is mostly, we do it in unstructured data formats. If we don't know the data, today I got an image, tomorrow I got a text, day after tomorrow I got some video, day after tomorrow something else has come. So it is very difficult to analyze. The machine cannot know what it is. So it only tries to look at what are the changes you are getting it over a period, and then it tries to predict, right? So mostly if you try to see, for example, there is, let me take the help of you. He always put good morning in the WhatsApp message. When he gets up, he'll put good morning in the group and he'll switch it off. So it is something like a structured data. So day after tomorrow, if you ask tomorrow what he'll give, good morning only he'll give, right? So today he has kept good morning. Tomorrow he has put some namaskar emoji over there. The day after tomorrow he has kept some sign like some drawing he has made, good morning, hi or something, and he kept it, and so on. If he is wearing that one, then he tries to observe what are the changes he's doing. Today and tomorrow he has kept like this. Tomorrow and day after tomorrow he has kept like this. So he based on that he will try to predict it, right? It is not on the training set. Okay. So there is, in supervised learning, there is not a good or bad answer known in advance. We don't know whether it is right or wrong. We'll just, based on the data sets, we'll try to put it, okay, this is good and this is bad. It is the variation from a group behavior that allows the computer to learn that something is different, right? So in the group, if you try to find out, there might be some people who are using text, some might be using emojis, some might be using GIFs, some might be using videos, some might be using some other content, written content, scanned content and all, right? So it can only say that in this group, tomorrow there might be 5 text messages, 5 videos and 6 videos and so on. Right? So now, I think I'll stop over here. We are almost close to 3:30, and we move on to the lab session so that some 3 or 4 routines are there, which will give, first try to run it on your laptop. Okay, we'll give the codes of the routines like a random forest. Sorry? Sir? Okay, gradient descent and okay, so decision tree algorithm and gradient algorithm and the random forest. These 3 will give you, and once you run the codes and all, if you are comfortable, we'll give you a data set, and we'll see how to allocate resources from the data set based on the data set, right? So we'll just take 10 minutes break and we'll come back and we'll start working on that. Okay. There are different types of requests coming in, and there is a signal strength for each one. And based on the signal strength and the latency, the bandwidths are allocated, and you can see that the percentage of allocation is done. Okay. Just set and see the variations in the data set. We have different types of allocations. It can be a video call, it can be a voice call, it can be streaming video, it can be emergency, online gaming, downloading, web browsing. IoT temperature is the different 9 types of data, which are, otherwise you can see that they are repeating. Or 9 or 10 types of data types are available to you. And you can see the signal strength of those calls, requests. You call it as QoS parameters. When a call has been admitted, the signal strengths are those things. And the latencies are the device which is sending IoT is far away from 105 milliseconds it takes to get that temperature. Whereas if you try to take a video call, it is taking 30 milliseconds to get that, which is by the means of latency, you can say that video call is nearer and the IoT is far away, device which is sending and so on. So you can see IoT data, you can see that it is far away like drone or somewhere. And video call and voice call, you can see that they are from mobile user who is nearby to the base station. Only the IoT temperature is far away, which is like a drone or a HAP or somewhere it is lying. Based on the latencies, you can tell them. And the requirements, if you try to see, the minimum bandwidth required is for IoT temperature only, where the data set is very small. And the highest will be for video streaming or video call. Sorry? Emergency service also needs bandwidth, but it is not that high as video streaming and all. Right? You can see the video call takes the highest bandwidth. right? So lowest will be the temperature sensor. So of all the group of video calls, if you try to see, only 70% is allocated to video calls, and so on. You can see at that instant what it is. So this is the data set which is in your hand, and now we move on to the codes. So you can see that you can, the important thing over here is the first line. If you try to see, there are three important commands you have to give at the beginning: import, pandas 1, numpy 1, re1. These three are important. You have to write for all the codes, right? And then you have to write model, sketch, assemble, pre-processing, and a plot. Okay, my plot you have to use for plotting the waveforms. And you are uploading the data set into the Colab your directory, and then you are loading the data set, remove the special characters in the columns, then you read the signal strength, latency, allocated bandwidth, and the resource allocation, and then you try to train the machine learning algorithm, and you have you are training with random forest model, and random forest is very good in case to find out any discrepancy in the data set, right? If you have any deviations from the data set, actual data set, that can be easily detected by means of random forest algorithm. Okay. So using that, you are trying to find out the absolute error, R-squared score, and accuracy of the algorithm, and the outcome, and then you are trying to So can you run and see the outcomes of it? So you can see the actual versus the predicted resource allocation. The actual one is the red one, whereas the predicted ones are the blue dots. So you can see at 70%, so many services, like we have 10 or 12 services in the set. So you can see that the 12 sets have been distributed such a way that the services 70%, these are the things actually predicted. Services have been predicted 75, 2 at 80, 2 at 85, and 4 at 90.
Your data set
So,
away from this one, you're trying.
And actually the red line is the line which has been allocated.
So it's even
So now the accuracy of the algorithm data set, the larger the data set, it becomes more accurate, right? So here if you try to see, you can see that video call, voice call, streaming, emergency, online gaming, you have different types of application. You can enter one application like voice as video call. minus 60 or 70. You can latency 10 milliseconds. So you can predict that this much resource is required if you have video calls around how many video calls you have given? Not video calls, which is the number of bandwidth units you are allocating to video call is only 10. If you allocate that much, you can see that resource is 72% resource have been allocated to it at that latency and that bandwidth. So now the total resources with you, you have to allocate for drones how much, for phone calls how much, for videos how much, for gaming how much, all these things you can distribute it and you can allocate it. Right? So you can see the allocations and you can vary the interest also. Right? If you want to allocate more for sensor data, you can pick up sensor data and you can give larger bandwidth for it if you have too many sensors and all. Right? So now please try to look into it for some time. We'll give you the next algorithm. No, కిందకి వెళ్ళాము. ఇంకా పైకి కొద్దిగా ఆల్గారిథం ఒకసారి. Yeah. So now we are trying to run the decision tree regression algorithm. So basically what we are trying to do is we are trying to form a tree and of the applications what we have, like video call and so on. We are trying to divide into 2 subgroups and so on, and going up to the root node, and then we are trying to make a decision on it. So the sets from the given 11 or 12 set, we are dividing into 50 and 50, and then again 50 and 50 and so on. So which means 5 and 6 on one side, and 5 and 6 and so on until we get the last decision node. So then we are applying the prediction algorithms and trying to predict the model out of it. So now we'll try to run this algorithm for the same set, and we'll try to see. So out of the 12 services what we have, you can see that one of the service was actually 60% requirement was there, and the actual is also 60%, whereas the other one, if you try to see, we have different resources requirement for 55, 65, 70, 75 and 85, but actually the allocated one is only 70. So you can see that the actual allocation and the predicted allocations are almost matching. It has matched with 6 of the outcomes than the 12 out of it. Okay. So you can apply for streaming if you try to see. Signal strength of 70 if you take it, and latency is around some 12 or 25 you can take it. So allocated bandwidth will be some 50. So as you can see that the values what we have taken are and the training set are not same. Right? The training set what we are given to the machine and what we requested are not same. So there is a small change in that. If you try to see the streaming, in the earlier case it is written 2 Gs, I think. Yeah, okay, 70, and the latency is around 25 or 20, and the allocated bandwidth is 5. So with 85% you can accurately predict the values, right? So when you are trying to pass on these values, it should be realistic in nature. You cannot give some arbitrary numbers and try to ask the algorithm to predict it, right? Close to the actual values you are supposed to give it. Okay, and you can just see for different services like voice, video and all, you can just manage to see if you are trying to use video services on your drone, so the latency values will be very high. So you can increase the latency and see whether it is predicting accurately or not. Can we move to the next algorithm? So we are moving towards the Picturing, I thought. Then, yeah. So now we are trying to move towards the gradient boosting regression algorithm. So, there is a model called as gradient boosting algorithm model. We are trying to use that directly the model, and we are trying to. So there, if you try to look into the ML, there are a number of models which are already existing. You can use them to basically start with, and once you have a grip, you can change the parameters and requirements for your application. So if you are trying to look for the data sets, you have a lot of data sets available in Kaggle. And the Kaggle, you have a lot of data sets where you can download. Otherwise, you can generate a synthetic data also. It is not that you have to download and do it. Based on the experiment, you can generate a data set and you can use it also. Taking long time. So now let us try on emergency services and see what it has. $70, 10, 30 or 40.
10 kbps to 15 mbps.
Yeah. Yeah, so with more accuracies you can predict, because it's emergency service, top priority will be given for that. And even the allocated bandwidth units, if you give more, it is fine. But since very rarely you get an emergency call, it is not that all the calls will be emergency. So we'll stop with this. You can work. Works what we have done, we will just try to put it up. So one is last year we have done, before last year actually, we have done one machine learning algorithm has been developed to predict the age-based risk, if he is hypertension or if he is having obesity or if he is having some heart trouble, all these things taken into consideration. We can predict that what is the risk of a patient. He has to give his weight, his body mass and his height, all these parameters if we pass on, he will get the prediction whether he expected to get heart attack or he is able to get some of the parameters. And for that, we got a best paper award also in IEEE TENSCON. And there is another work what we have done is resource allocation over a bandwidth constrained linear vehicular networks. And this was also presented in IEEE Bangalore, some conference name I have forgotten, but it is there also we got a good response with this paper, where we have taken only a linear network. We don't have multiple roads and all. And there is another algorithm which we have presented in vehicle to network resource allocation using Q-learning and random forest. And there also we got a best paper award for that. And here, especially in this, we have used two learning algorithms cascading one top of other and trying to use for better allocation of resources. And there was another project done by one BTech student only from Kids College, I think. He is actually third-year student who came for summer interns, and he has spent 2 months on this. And we also presented this in IEEE ISS, and there also we got a good response for this. So here, there are like a lot of gas sensors and smoke sensors in the colony, and whenever there is smoke or something, it has to detect and inform the fire station so that they'll come and put it out. The other one is, this is again a payload allocation only, which we are trying to use to maximize the efficiency of a network. So this is one more work which we have done, and this also has been published in the IEEE journal paper. So these are some of the works which we have done last year, not this year. This year we are supposed to get some more. That is on the microprocessor front, sorry, machine learning front. This is the assignment one. Yeah, my base station is located.
Sir, after go ahead. Sir, after reading this, I got that only our lead tower is operational and the rest of the towers is non-functional. And the radius of that particular island is 25 miles, and our those coverage area is 5 miles. So I will, according to my idea, that I will cover first circumferentially. If we will talk about the circumference of that particular island, that will be 55. 55. And if we will talk about the coverage circumference of the coverage area of our drones will be 10.5. So we will report five drones, and in the circle of concentric, we create one circle more inside the flow zone, and we will put 5 drones there, 10 drones, and our communication will be established that like this. that air-to-air radio communication from air to air, and backhaul connection from backhaul connection will be connected like this, that drone to drone, and our mid tower is operational, sir. So I will use the core network as a operational mid tower, and from air to air, drone to drone, and drone to that tower we will communicate, and that tower slowly it is communicated through the base station. So we will see the data from there.
Yeah, first of all, the question is very open. Just want you to see how you can respond, how you can think. So it's not, the answer is not just one. There's no one answer. Okay? But what's your name, sir?
Sumit Kumar.
Sumit Kumar suggested, or assume that the center tower is operational. So obviously, when it is operational, it's possible that it could be connected to the mainland, or both are possible, isn't it? Because when you have suppose when we have 5 centers, then it's possible that the backhaul might be coming from any one of them. Let's say, for example, the center one is 3. We have 1, 2, 3, 4, 5. This third one is what you are referring to. It's possible the third one could be connected to the mainland, or maybe the first one or the last one too. Okay? Assuming that in your case, what you are assuming is the middle tower is connected to the mainland. That means backhaul already exists. Backhaul is already there. All we need to worry about it to replace that. So your point is correct. And make sure that you understood that radius is 5. So that means your diameter is 10. That hopefully you assume that. So total area is about 25 miles. So the diameter is about 50. Right? And it's okay if you have other calculation, but the intention of the question was you have 50 mile wide. Right? If you look at the diameter, okay? But then each cell has a radius of 5. When I say 25 mile radius, the diameter is 50. So obviously still it's 5 cells only. You need only 5 cells because each cell will have 10 mile diameter. So ideally you fit about 5. With that part is correct. So there are 5 cells. That part is correct. Yeah, only one is right. So you are assuming the middle one is functional. And you are also assuming it's already connected to the backhaul, so we don't have to worry about that. Okay, that's one. Very good. But if you look at carefully, one more catch is that I think Dr. Prakash and myself, we were earlier thinking how many circles you need to fill in. So just if you take a 25 mile radius, will 5 sufficient? Can you just look into it? For example, let's draw a diagram. But this question is motivated by Dr. Prakash original thought.
So you have a larger circle, a small circle of 5, and this is 25. So how many 5s are required to cover the complete area?
So the radius is 25 miles. We calculate the area of the total circle. So if we ignore the pi, then 25 square by 5 square would give us
Number of circles.
25. So it would be the number of circles.
So now let me draw that figure. I mean, look at it carefully.
Yeah, one more thing, in the original question I said there are only 5 cells. Yeah. In the beginning, like in the question I said there are only 5 cells. So that was also intentional. We just wanted to say there are 5 cells. Which means that we are not really, the whole circle is not really completely covered. Okay? To begin with, it's not.
Actually, this might provide more coverage than cell towers.
Sir, okay, go ahead.
Sir, after 5 cell towers, we just go inwards. Our diameter will
In
be
a
lower.
linear way, if you take it, there is a free coverage.
Yes, sir. Then inward will flow, then diameter will be reduced by the main radius. Means 25 minus 10. Our diameter of
So 25 minus 5, radius you
No,
are not talking about area.
yes, sir. 25 minus 10, sir. Because here our yes, sir.
Linearly if you take.
Yes, sir.
So
Nearly.
50 by 10 is 5.
Yes. 25 minus 10 is 15, sir.
No. I think, actually, no. I think there is a lot of room for confusion, but let's see. To begin with, I use a different color. So the question itself has not really covering the whole. Just only 5 cents. So each one is. So I'm not really covering the whole. If you linearly arrange, no, this is one of. There are other options too. How you place 5 cell towers within a circle of 25 radius. There are many ways. So that means to begin with, we are not really, the problem itself is not given, problem is given in such a way that, okay, we are only having 5 cells. So that means it's not fully covered to begin with. Okay, so that's, so not, you can place them anywhere. I mean, based on the question, if you follow the question, just per word, the whole area is not covered. So which means that this 5 can be placed this way, or maybe this way, or another way too, isn't it? All right. And then I said one of them is working, so maybe the center one is working as you suggested. Sumit suggested. You need to figure out only taking care of that. But Dr. Sai Prakash's question, original question that when I had talked to him, he was saying how many cell tower you need to cover the whole thing. So even you try to put maybe fill up with this circles, there will be gaps unless you really overlap. There will be gaps. So, but to begin, your answer was correct in the sense. With the assumption that you made, your answer is correct. Okay? But there could be many other answers. So just because this is what I had. But then obviously there are a lot of gaps.
No, thing is, see, the small itself, you can think it as a drone area. How many drones are required?
By the way, I was right. Each circle actually is a coverage.
Age of the drone.
So if we go theoretically, then 25 crores will be necessary.
Yeah, you need 25.
Yes, sir. Theoretically. But that theoretical will not cover because circular area. So
Our regions are.
all cover 100.
Or else we can take turns and change the formation so we can cover all the drones. But it wouldn't be covered at the same instant. We can take turns to change the
That's also another option. You're right. Just because we talked about it in mobility, that's the significance of mobility.
Can we be this actually be seen after the time here?
So you can use one cell tower, just one flying base station to go around like mix up, maybe concentric cell. That's a significant option.
4, 5 more and rotate.
Yeah, you can have one arm, even with one. In one of the discussions, we talked about TDMA kind of approach. Like you use some time period T and divide it into small intervals. So basically, you're making your own set. That's also an option. So if the question was given to just make you think of it. So one solution is what what's your name? Varun solution also is
Sir, so if we use this FPMA and if the drone has to, keep circling on, will power management again be an issue? Just again, if it's keep on changing the drones or recharging them more frequently compared to, when they are static or like.
that's true. If you are what's your name?
Others.
Others is saying it will be challenging to manage the replacing the drones and power management. But for example, in the paper,
Also, if the center of the mid station has a cell tower operating, there must be power connection. So why not add some tethered, from the ground to any minimum only just 2 drones. So for the surrounding connectivity of Delta, the mid drone, and then away from that, you can use this circular pattern.
So it depends on the assumptions we make. In the case of
assuming
in the others, Varun, what in the case of Varun's assumption, if you are moving, that means you are not tethering. So if you're not tethered, then it will be the lifetime management will be a challenge. But if you assume that theoretically, okay, you have a lot of what is the flight time is unlimited if you make that assumption, which is not true, which is not practical. But in theory, if you assume that it has long battery or infinite battery, we make those assumptions just for conceptual understanding the concept. Even in the discussion we had, we assume that you can move around as long as you want in the discussion. In fact, probably at that time we didn't even discuss what if the power is flight time is limited. So as Varun said, it's possible that we have one going around, and when the battery is exhausted, you can send another to replace, and then keep doing this. So ultimately, you are mimicking this scenario where you have infinite flight.
One more solution is that if we, kind of introduce the areas where you said there will be no coverage, and then we also increase the converting of redundancy. So let's say we have 16 drones in this case, only 8. I'm assuming this is this what I thought. So 8 will kind of cover the island, in the sense of north, south, and east, and west, and northeast, northwest, southeast. So that way you have 8. So even if there's some overlap, they'll always be moving. This is one. And then the other part of the 8 drones, which will act as a backup. So to address the power situation over here, let's say each drone has 12 hours of power reserve. So when the 8 drones are flying are having low battery, then the other 8 can take off. And when since we assume that the tower delta, which is in the center of the island, has power because it's working. So even if we don't have a satellite uplink, I am going to, if we assume that we don't have any connection to the mainland, then we can use a satellite uplink. So even if the tower, okay, that's one more. I'm just going to introduce one more thing. So if the tower does not have the equipment to communicate back to have a backlink back to the mainland, then what we can do is we can add a satellite dish to either 8 of the drones or 2 of the drones in such a way that when the 8 drones which are either charging using a tether, the center of the island, they have satellite uplinks. So either 8, which is the 8 which is charging, or the 8 which is flying, they will be connected by LoRa. So using that, we can add the using the person who need to make an emergency call can either make a call back to the mainland using this tower or using the Wi-Fi call VoLTE. That is one, and one more thing is that
Let's take one by one. I think the first thing is in case of Sumit's solution, we assume that the background is there. Background is working. We could ask what if the background is not? Background is not. That means you assume that the tower that is alive is connected to backup. But you can create a scenario, or you can think about a scenario when what if it is not a backup? There is no backup. That means the one with backhaul is dysfunctional. So you need to come up with a solution for the backhaul. And for backhaul, what are the options?
use satellite dish and connect it to LoRa. Sorry,
LoRa really
not
LoRa
Lower,
really not.
connected to a low Earth orbit satellite constellation.
So you're talking about
For
LEO satellite.
Yes.
But LoRa not for
LoRa is-
not.
LoRa is just for UAS to UAS communications between the eight zones.
Okay, again, when you say LoRa, are you referring to long range thing or satellite? Is it satellite or?
I'm referring to LoRa in this case, which is for UAS to UAS communication. That's a long range. But then to
Let us skip on to the.
Yeah. Let's skip. I don't think LoRa actually is a good solution. Okay? LoRa is basically
We cannot change the configurations of the base station. When given a base station, what are the options? And the first case, let me take one.
but
When he said truncated circuit,
coming
lose the contact with the base station once you go away from 10 units. So that only works for up to 10 units of distance. Beyond that it will not, because it is 50 or 25. So you can go only up to 10. Beyond that it will not get that. So minimum of 2 are required for the covering subject.
So then we can use the nearby drones as repeaters.
Whereas you are keeping only one and you are rotating around.
No,
Sir, so that's what I said. So near to the base station, up to like 7 or 8 miles, you can have a tethered drone and then use that as the
That
receiver.
hopping you can use.
Hopping.
Hopping you can use. As you were saying, one with the case at case. It will only go up to 10. Beyond 10, you lose the contact with the base station.
because the radius is by
That's what we have defined in the problem.
What if we use let's say, within the 5 mile radius of the mainland tower, that is tower delta, we are connecting a drone on each side of on each direction of the island. Let's say east, north, west, and south, and then so now all the 4 drones are inside the coverage radius of the delta tower.
Yeah.
And then from each drone on each direction, we create an ad hoc system to communicate within the drones so that they cover the entire area on each direction.
No, we are not asking how we do it. How many drones are required?
Here I'm using 16 drones.
So you are
4 on each side.
16 drones
4 on each
which
side.
cover everything, right?
Yeah.
But he is saying that 2 drones are sufficient which are rotated up. So the debate is how many drones are required
Yes.
per given time.
So in my case, it's 16, sir. So 4 on each side, so that they cover the entire region. So let's say each drone has a 5-mile radius for the communication range. In the ad hoc system, if we keep each drone on a 5-mile range, then it
So
can be
the
able to
problem
cover.
of that is, until the base station can connect if a drone is lying within 5 units. We have not defined what are the units, but if it is 5 units, it can come.
Okay.
So the other drone it can communicate. If it is 5 only, it's not 10.
Yeah, it's 5. It's 5.
It is 5.
It is 5.
So now you count how many 5s you need.
Let's say
So to bridge that you have one LoRa be
So
20.
on a line you need at least minimum of
20.
no
25.
see 25 is your line, and you have each one is 5.
So it's coming 20.
So 5 only. 25. Radius is 20. At each 5 point if you keep it, you get 5. So 5 drones have to be there on the radius for it to go around and cover the complete area.
No, sir, they are static.
You want to keep it static?
Yeah.
No, even static also.
You can keep it in a square shape so that
There is no square, right? It is circular we are trying to show. See, we cannot change the technology.
No, I'm saying about the ad hoc system, sir.
he's saying
No,
everything
we are
under
not
the
talking about it. We are trying to solve this. Right? Even a base station, one of the base stations in there. We are trying to see how many drones are required for covering the complete region and how. Temporary.
Did you draw a picture?
Okay, you have drawn the picture, right?
So in general, there are 2 options. Right? One with a moving drone, and one is enough. But the problem is,
So the drone can move only on the 5 units circle. Cannot move around it.
yeah, assuming that the center one has a black hole connection, you can
move on the circumference of 3.
okay, why don't you go ahead?
Let's say this is the our delta. Now from here, which is 5 mile radius, I'm connecting the node on each direction. And then from here I'm creating an ad hoc system around like this. Like this on each side. So that they cover an entire region for here. If we do similarly to
all the 4 sides.
all the 4 sides, then even this could be linked.
But the problem over here is, he wants to do it with 3 or 4 drones, and you are using around 4 into 4
No, let's
16
take
drones.
our concept.
No, the problem over here is we are only looking at number of. So if you take 16 drones and do it, it is fine.
Yeah.
But he says that my solution is only 2 drones.
That could be difficult to cover that.
But your cost involved is almost 8 times the cost of his idea.
But what I'm saying is,
See, there are, as I told, there are a number of solutions. Each one have their own assumptions.
Each node has 5 main.
No, the problem given is there are one base station. Right?
You are still that will not cover all the days.
If it is rotating, it can cover.
But it's saying static.
Static.
Okay, let's do it. What you are missing or what you need to do is place them in such a way. I think what that let's say just like the way I put earlier. So suppose you keep 2, 3, 4, 5. Assuming that this is about you're talking about here you're using drones.
Yeah.
Okay, right. Fine. So what the assumption is there are drones. The drone is up somewhere, and this is the coverage. So you need to keep in mind that you are filling the area with the coverage. So now think about how many. Think about the coverage area. Yeah, let's try to fill up.
In between.
So we covered this, right? So how many, so basically the question that Prakash had in mind is, how many circles are needed to fill up the whole hole?
That's what the answer of what Warren has told is, take the circumference of the outer circle, take this the circumference of small circle, divide it, you get
You mean the area?
area.
Yeah, I mean,
The bigger area by small area,
Bigger area.
reduce the number of
yeah, like it's like pi r
square
square.
by small r square.
So that's what it is, right? So
Particular by
it's not about you're thinking this is the drone, but we need the coverage area, not the.
number of drones.
So you are referring to this is the net factor. We need the. But in that case, maybe.
so this is actually covering 20 miles, right? So here is
Okay,
5.
I think we will let's do one thing. I think let's look at tetronic points. Okay? Let's do this. Well, if you think about a drone is like a point, whereas the coverage area is a so not really like put a point and then see what you have. That has 5 now. Put it.
No, the circle as
Like,
height.
yeah, something like this is the circle of 5. So it's more important to look at the coverage area, not the, and that should be at least 5. Yeah, see, like, or you can say just put a point. Just put a point. Then you are saying my distance is 5. Okay. So how many? 1, 2, 3, 4, 5, 5. Well, actually, it's supposed to be 5. The circle has.
Radius is 5.
Okay. radius.
Diameter.
So okay, that means what you're saying is this is my, and then if you have this,
It has to intersect.
it's like intersect. Is it adjacent?
Yeah.
Can you try to tell me what you have?
Okay.
Yeah, that's that next.
First draw for the inner one. That is outer one. Inner one you have left one. That's why you have not drawn. That's actually the outer one. No, not.
Yeah.
Between so now you can draw maybe.
Now it's 3 comes forward.
On the circumference you can draw. Draw if you lay on this.
16 to 25 rounds.
Structure Prakash. Is this the fact 100 satisfied?
Yeah, very in number of circles.
So like this,
So how many drones you use? How many? With 16 you can cover the whole thing?
One line, how many? One diameter, how many? 4, 5. 4 that side and 4 this side. So 9.
this is one.
So directly can just rotate.
You can according to the
So 5 in one circle there will be 5. In inner circle there will be 3, and at the center there will be 1. 5, 3, 8, 1.
4 and 4, 8.
Yes, sir.
Will that cover the whole circle?
No, only line.
Only line.
Yes, sir.
How many
Overall,
overall?
how many diameter you need 8?
Diameter
16? I mean, no, but 16 could cover the whole thing?
No.
Not there.
16 to 4.
But only this area.
Sir, we can rotate the whole.
Okay, what about
body.
in between?
That's what I'm saying. You can rotate, but with one it is not.
Nice.
4 in there, you can rotate it periodically.
Yeah, we'll actually, why don't you think more at home and then you can also bring it back. So maybe one idea for everyone, just write your answer. But think through it. First thing is cover it. You need to cover. Make any assumptions, but make any assumption that you want to make. But make sure that you are able to cover the whole. And even whatever, right? Can you also work more on it and then how the coverage is, right? So once again, the answer depends on what assumptions you make. And in terms of background, remember don't forget about satellite is an option. Also there are in-band communication, meaning that each drone from its available bandwidth allocates some percentage for connecting with other.
Call it as in-band communication.
You can read it.
Total bandwidth, we leave some portion for command purpose, some for data.
And you can actually read about it. If you found search for it, you can see in numerical. Look for a numerical example. In-band communication, then you'll understand that.
I'll put up the second as
Maybe a good thing to do is let's compile all the solutions. Okay, each one, if each of you or maybe two of you can work together and come up, send it to us, and we'll try to create a nice solution. Yeah, and then see what are the pros and cons of each. For example, less number of drones, but connectivity is limited.
so cost effective, that's number of.
Yeah, that's
Our electrons, they might have more number of. Depending on the
just for fun. let's do it, just do it, and then you can actually share this information even after the work. Doesn't have to be.
So the second one is we are trying to look into, given a wireless communication channel, we want with a bandwidth W, can we do better to speed? Or do we need this one to do the problem? We don't need that.
No. It's up to you now. Yeah. Yeah. We can.
Huh?
Yeah.
Switch off. So we just want to find out, given a bandwidth constant,